Okay, we are live now. So, good afternoon, everyone. Esteemed judges, SG Innovate, and also our finalists as well. So, welcome to Deep Learning Datathon 2020 finale. My name is Christian. I'll be the host for today from AI4IMPACT. So, I think the program for today will start with brief introductions and also followed by some sharing from our submission partner, Caitlin, and also followed by presentations from all the finalists as well. So let me just start as well, just to give some context on on the participants' journey so far, right, from start of Datathon till the end of Datathon. So it's been a ride, a very bumpy and very accelerated ride. So basically, like most of you guys, I think, start learning data science. Most of you from this Datathon, and most of you have some experience beforehand. And after that, right away, we throw you directly to the real world problems. You guys actually managed to solve, lots of real world problems along the way. And then also, like throughout like these 2 weeks, you actually managed to learn lots of neural network concepts and apply it and deploy it to create a live predictions. So I think just for your audience who are watching this on YouTube, the problem set actually is to predict wind energy output, and then as a feed for live energy trading. I think the objective is to make sure that the models actually are forecasting the output accurately, and so that the energy company can have a stable supply of energy through their forecast. So this is based on live data from France, and I think the students have been. These are the chosen 10 out of 60 other teams who are also deploying the models. So if you guys want to hear from the best, I think listen to this what they are presenting, and also listen from the opinion from the judges as well, because they are the one who give insightful feedback on how machine learning models are supposed to run in the industries. So yeah, they're doing very well, learning deep learning from scratch, developing it, deploying it. A lot of sleepless night we foresee because of the Telegram chat at 1 a.m., 2 a.m., 3 a.m. So I think a big kudos for you guys who have managed to build the models. And yeah, let me also share opportunity as well to introduce our judges as well, who have actually supporting us and spending their afternoon today to just provide their feedback and guidance for the students. So the first one is of course Mr. Hanif Bakshi. So Mr. Hanif is a CTO of Humani, and he himself has 15 years of experience building ultra low latency, high throughput, highly scalable and resilient applications for banks, hedge fund, and startups. So if you guys want to learn, actual deployment, Mr. Hanif is the right person to go, because you have to be high throughput if you are working with hedge funds and banks. So yeah, he was the head of tech of MDEC, a fintech company, a global fintech company, and his passion lies in creating simple yet optimized solutions which can scale and stand to the test of times. I think simple and sweet and effective is the right way to go if you want to deploy your deep learning models. Make sure that actually it's not just understandable for you, but also your stakeholders as well. The other one is Dr. Mikhail Filipov, Dr. Misha. Yeah, Dr. Misha is a unique one, has a very diverse AI background. He is a chief scientist of Quote AI. So in Quote AI, he's applying NLPs, natural language processing, deep learning and statistical models to explain source code in plain English. But he also as a mathematical physicist, he studied the dynamics of complex systems and has built mathematical and AI models for tsunami predictions, tropical atmosphere, the housing market, historical information, and visual cortex of human brain. So if you want to see how deep learning is applied at different industry sectors, at different segments, Dr. Misha is the right person to share his insights on that. And of course, the third one is Mr. Arnold Dore. So Arnold is the head of AI of Terra AI, and also one of the co-founder of AI4IMPACT as well. He has 20 plus years experience developing a weather forecasting system for mission critical offshore operations, when the sea level can be as high as 11 meters, and when the wind can actually blow, the tide can actually blow entire building out. So Arnold works with companies including BP, Shell, and Chevron to help them save lives for their offshore staffs. And through AI4IMPACT, Arnold has enabled also like thousands of university students and also professionals develop AI for applications for solving industry problems. So here is some introductions about the judges as well. And yeah, so we still right now moving forward, we do have an interesting speaker right now from SG Innovate Summation talent. So I'd like to welcome Caitlin Ng from Poly B. So Caitlin Ng actually is a year 2 mathematics students from NUS and also a champion of our previous Datathon. So IT Datathon 3.0. Our past joined Datathon with NUS. So the challenge right now at that time was actually to use IoT data to forecast dengue 18 weeks ahead. Yeah. So now she's currently working as a summer intern in Poly B, and through that Datathon experience, she's also managed to share her expertise as well as I think as a data scientist for Poly B, SG Innovate Deep Tech Startups, and for sure her sharing will be very helpful for you guys who are actually looking to for internships, and deep tech internship opportunities. So maybe I pass the time to Caitlin to share her experience. Caitlin, please.
Hi everybody. Okay, just let me bring up the slides. Give me a moment. Okay, so can everybody hear me? If you can hear me, give me a thumbs up. Yep. Okay, great. So hi everyone. I'm Caitlin, and thanks for giving me some of your time to talk about what I've experienced for the submission program. So just a little intro about me. I'm a robotics fangirl, so I really like robotics, and I like trying to integrate AI into robotics. And I also like bouldering, so if any of you want to try it out, you can hit me up. And I like listening to jazz and indie music. So I'm an NUS year 1 going into year 2 CS and math student, and I decided to take part in IoT Datathon 3.0 at the end of year 1 during the winter break. So afterwards, I went on to join the summation program, which I'll talk more about later, and I took up a robotics internship at Poly B. So for my IoT Datathon run, which was from like December to February 2020, we had to perform dengue prediction and make a website showcasing our work. So the website is actually still running. If you want to check it out, it's mozinet.io. The link is here. And this is my team. So there's 3 of us. It was a very enriching experience, and during the actual Datathon itself, very much like today, some people from Summation program came down to talk about. Some people from SG Innovate came down to talk about the Summation program. So so I decided to sign up for it, and after a few rounds of interviews with different companies and with SG Innovate, I ended up with an internship at Poly B. So today I'll just be sharing my experience at Poly B through the submission program, and hopefully this gives you guys a better idea on how it's like to be a submission program intern, and maybe encourage you all to sign up for it. Yeah, so my internship lasted from May to July 2020, and as you guys know, there was a whole COVID-19 situation going on at this period, at this time, and the circuit breaker period coincided with the internship. So so a little bit more about Poly B. So as its name suggests, Poly B is a startup that aims to provide pollination solutions for the agriculture sector using drones, and especially for hybrid seeds and indoor vertical farms where they rely a lot more heavily on hand pollination. So my work consists mainly on autonomous pollination, where I aim to improve the flight performance of the drone by investigating different detection and control strategies, and also try to build up the autonomous pipeline of the drone pollination system so that we can start experiments as soon as possible. So the first month of my internship was actually work from home, and it's really difficult to do a robotics internship from home. So it's hard to have it was hard to set up a proper test bed for the drone, and I ended up with a mahjong table as my workspace, and I strapped a $200 camera to the window using an aluminum rod. So it was fun to try and work around the situation, and luckily there wasn't a lot of collateral damage by the end of it. So I was able to make some improvements to the flight performance in this period of time, but the true test really comes when we're flying in the actual indoor vertical environment, a vertical farm environment. So I was really lucky to be able to return to the office in June and July, and I was able to meet all my colleagues at Polyb. So working with them is definitely a lot more fun than working at home. And having access to our own little vertical farm setup really helped to speed up development and iron out issues that we have with the drone stack. So I'll say that for me, the best part of my internship experience at Polyb is really working with the people, because a good team really makes the journey of chasing a difficult and faraway goal a lot more enjoyable. So I'll say that it's important to look at the team when you're looking for an internship. So it's good if you can go down and talk to the people there just to get a feel for the culture of the team. So of course there was a lot of work to be done, and I ran all sorts of experiments to test out different control systems and ironing out bugs in our code base as we were building it up from scratch. So being in a small startup, there's always more than enough for everyone to do. So it can get quite hectic at times. So since the start of my internship, the drone stack actually went through multiple revisions to improve the accuracy of detection. So here you can see right at the start, there were a lot of issues with the control where it would just randomly flip and fall to the side. And we tried to investigate what makes the drone hover better and what makes it what environments make it worse, to see how we can improve the performance. So as we are also working around plants, which are very delicate, it's super important to get the drone really stable and reliable. And to get there, I've actually made a lot of plant confetti along the way, just shredding a lot of plants. So you can see in this video, a plant leaf just flew by, and that's a very common occurrence in my work. Yeah. So this is a video that I took towards the end of my internship, where it's a video of a drone hovering over a tomato plant flower, and returning back to base. So it's still far from perfect, but we're slowly seeing improvements, and hopefully we can start having pilot trials soon. Yeah, so it successfully landed. It's like really happy. Yeah. But other than all the work that had to be done, there was a lot of fun to be had also. So um, so being in a startup that develops solutions for the agriculture sector actually opened up a lot of new and interesting experiences that I probably wouldn't have had in a different startup. So as I worked very closely with the horticulture team at Polyb to run the flight experiments, I got to actually get my hands dirty helping out with the plants too. So it was really exciting for me to see all the strawberry plants come in all at once, and we have to pot them and put them into the vertical farm system that we built ourselves. And it was even more exciting to see flowers start emerging, and so that we can start performing our experiments. So in a few weeks' time, the fruits from the first few flowers that we pollinated with the drone will be coming out. So that's something that we're looking forward to. And here you can see my extremely ghetto table setup using a cardboard box to get the laptop nearer to the drone. Yeah. So I got to also play around with a lot of cool tools, because being in a startup, there's a lot of there's a lot of improvisation that needs to be done, and we actually built our vertical farm system from PVC pipes ourselves. And here's a trip to Gardens by the Bay that I tagged along with to do some drone imaging. So it was really fun to be able to roam about without anybody there yet, because the cloud forest wasn't actually open yet. Yeah. So from the internship, I actually had the opportunity to learn a lot more about a field that I'm not usually involved in, which is the agriculture sector. And that was really interesting. And I think it's a unique position to be in, to work in the tech industry, because the tech industry is usually tied in with a lot of different industries, that like agriculture for one here, education, or the medical industry for example. So we actually have a lot of opportunities to explore different sectors, and it's a valuable opportunity to take. So for my internship, I also found that it's important to observe and critically reflect on what you're doing, and also set small goals and treat everything like a puzzle to be solved. So this keeps the motivation going, especially when there's a lot of work, like in a small startup. Yeah, and finally, a good team really speeds up development and makes it so much more enjoyable. Yeah, so that's the end of my very short presentation. If you want to know more, you can add me on LinkedIn. And this is my tele handle, so you can just tele me if you want, and I'll be glad to answer any questions you have. And just a shout out to all the SG Innovate programs that are available. So the Submission Program and Infinity Series are internship opportunities for talents who like to gain exposure in deep tech startups. So, for example, Polybee is a deep tech startup where we're trying to develop farming intelligence. So a submission program is also open to fresh grads with an attachment period of up to 12 months. So if there are any fresh grads here, you can consider going for it. Yeah. So this is the contact information for SG Innovate, and this QR code will link you to the website with the internship programs that they have. Yeah, so I'll leave this up here for a while. Thank you.
Okay, thanks so much for the sharing, Caitlin. So I think just to add up to Caitlin's points, right? I think for us as well as AI for Impact, we also would like you guys to actually always continue your deep learning, your data science journey along the way. And one way to do right what's after competitions or what's next for you guys after competition is also to understand how industry is applying data science on AI to drive some real world value. So one thing that we always been doing is actually to partner with deep tech organizations like SG Innovate and also other startups all around the world, right? So that you guys have also like not just after you showcase your skills, right? Because I know that right now we have 450 students of actually coming from all over the world: Singapore, Malaysia, Hong Kong, Kazakhstan, Indonesia, um, Nigeria as well, and also from Jordan. So and UK and US, a lot of you guys are spread all over the world. And right now, how you are able to actually grow your own data science portfolio is also to apply for internships programs like this. Most companies are open for remote internships, so you should explore. And if you guys want to get connected with companies who are hiring, also like don't forget to let us know, and also connect SG Innovate as well, because that's how you grow your own portfolio once you to prepare yourself before you even start working. Okay, so thanks so much, Caitlin, for the sharing. It's a very fun sharing as well. So let's move on to the first participants, first team. So AI, the first team is AI traders, and for AI traders, they are actually one of our top 10 who are making profits out of the energy trades. So if you want to hear the secrets of their success, tune in right now and pay attention to them very carefully and ask them hard questions as well. Okay, the floor is yours, AI traders. So get ready.
Good evening, everyone. My name is Mihir, and presenting alongside me is Suyash, and we will be presenting to you on behalf of Team AI Traders. So, owing to the incidental shift we as a global community are facing towards adopting renewable sources rather than non-renewable sources for energy production, this year's AI4IMPACT challenge revolved around forecasting wind energy production. The major stakeholders in the wind energy market and the simulated setup we were provided with were energy traders, wind energy producers, and energy grid operators. Our main objective was to play the role of an energy trader and maximize profits by getting a T plus 18-hour energy forecast every hour. So with regards to establishing the vital domain knowledge base, it was imperative that we create a model which is not only sustainable, but also reliable, and therefore takes into account the following objectives and its reciprocatory solutions. Firstly, to maximize profits. Secondly, to ensure liquidity by maintaining a sufficient cash balance to support in an event of an anomaly. Third, maintaining consistency. And by this, we mean that we wanted to ensure to constrict over predictions due to the embedded 2:1 or the 100 cent to the 50 cent loss ratio ingrained within the trading algorithm. And lastly, to minimize risk by fixating our lower bound prediction to avoid excessive underprediction. Then, for a prediction pipeline, we first collected all the raw data and moved towards cleaning data, which involved handling missing values by interpolation and aggregation and consolidating all the data thereafter. Then we conducted an in-depth exploratory data analysis to understand better the underlying trends. In the prep stage, we normalized and fused the data as per our needs. Then, in the windowing stage, we windowed the data and conducted feature engineering. Next, in the training stage, we defined our model and made attempts to minimize our risk. And finally, in the prediction stage, we used our training data to make predictions for the required lead time. So as part of our exploratory data analysis, we first took the clean data for the three variables and plotted these histograms. As you can see, for wind energy production, the distribution is heavily skewed to the left. For wind speed, we did get a bell curve, but again, it was heavily skewed to the left. And as for wind direction, there was hardly any trend that we were able to deduce. Next, we plotted correlation matrices between speed energy and direction energy. And using the Pearson correlation, this analysis allowed us to deduce that while speed on the one hand was highly correlated to energy, direction on the other was hardly correlated to energy. Since we also had two models, each from the 8 different farm locations, we decided to plot independent correlation matrices for both the direction and the speed data to understand the underlying relationship among these 16 datasets better. We observed that the values were highly correlated and similar in magnitude. This in turn allowed us to average them and create two datasets, one for direction and one for speed. As for the annual trends, there was a very distinct increasing trend that we observed. And also the production in 2019 was almost 2 times the production in 2017. With regards to the monthly trends, the very important observation we made was that wind energy production was very high in Q2, that is quarter 2, and quarter 4. Now, we use that observation to plot the average hourly energy production to deduce any underlying seasonal trend. Now, for the purpose of doing this, we use the first month of every quarter. Now, the hourly trend shows that the wind energy production on average depends on which month the production is happening in. For example, while the trend in April and July are following a very distinctive W and V-shaped trend respectively, the trends in January and October are relatively flat. Henceforth, we use this past month data to determine which month we were in exactly and the daily data to capture the irregularities in the trend. This in turn allowed us to predict a much smoother trend of what the actual values were. Then, for data normalization, we tried different scaling techniques from min-max to Gaussian scaling. And as it can be seen from the diagrams that we have provided, Gaussian scaling fit the data set much better and reduced the effect of outliers as well, as compared to min-max scaling. We also further divided by 2 to reduce the range.
We then worked on the windowing and feature engineering of our model. For our naive model, our sole objective was to beat the persistence, for which we included the hourly difference of energy production and wind speed. We also added features to capture the forecast of the wind 18 hours later. All our feature engineering was tried on a very basic network architecture, and we observed a test loss of 0.0935, which comfortably beat the persistence calculated. The lagged correlation graph and the scatter plots, however, had highly varying results. In our subsequent attempts, we then tried to incorporate features which captured the seasonal trends explored during our data analysis. We added momentum and force for the past 2 days to capture the movement and the rate of movement of the energy produced. We included skewness and kurtosis to capture the irregularities. We also added raw production data and statistics such as the mean, standard deviation, and range to learn the daily trend. We obtained much better results with a test loss of 0.055. The prediction graphs, as seen, also improved significantly with the smooth lag curve having a zero peak. The scatter plots also were now much more consistent, and the results were very close to the x equal to y line. We further tried out myriads of features in order to reduce our test loss and better our prediction graphs. And here is a list of our final set of features. Some of the notable additions were the inclusion of the statistics of the past month. We also smoothened our neighbors in order to reduce noise. These additions led to us receiving our best test loss of 0.044, which beat our persistence by a relative margin of 60%. The lagged correlation graph had a smoother curve, and the scatter plots now had optimum results, with values being much closer to the x equal to y line. The test scatter plot indicated that our model slightly underpredicted, which was ideal for us as the trading algorithm penalized overprediction heavily, and our objective to build a consistent and stable model was achieved. Here is a visual representation of our final neural network model, which summarizes our entire approach of building it. We believed that we constructed a proficient model which avoided large fluctuations and led to us being the only team that throughout the trading period maintained a top 8 position in the leaderboard as per our objective. Our safe and sustainable model makes it much superior in the longer run. We heavily experimented with the network architecture and deduced that the network of 4 layers and a base size of 128 gave best results. The ideal weight decay and the dropout probability was found to be 10 to the power minus 4 and 0.025 respectively. We tried out different loss functions and regularization types. We also experimented with methods such as scaling and autoencoding to modify our network accordingly. Our model has certain limitations. Firstly, it underpredicts by a large margin during high production phases, possibly due to the inclusion of the 2017 data. Secondly, it fails to efficiently capture a downward trend, which could be a result of lag and smoothing the labels. Lastly, our experiments with calculating the sine and cosine of directional data was unsuccessful, and we were unable to deal with its circular nature and efficiently standardize it. We believe that we can further improve our model and overcome these limitations, since the frequency of higher production values is low due to the inclusion of 2017 data. We could optimize the loss function such that more weight is assigned to these values. We could also use a different loss function that penalizes overprediction much more. Lastly, we could also shorten the test data set to better understand the performance of our data on live data, performance of our model on live data. We tried incorporating the aforementioned suggestions by implementing different loss functions and assigning more weightage to higher production values. The test loss significantly improved by a relative margin of 20%. As you can see from the plots, our improved model had much accurate predictions for higher values, in addition to lesser occurrences of overprediction. This ultimately led to greater profits. Finally, after having worked on this project for a month, we feel that this experience was more than a competition. To further develop our interest, we have created a web application which displays our model, real-time results, and its predictions. We're constantly learning every day by improving the model and the web application. Lastly, we would like to take a moment to thank the AI4IMPACT team for giving us this opportunity and truly inspiring us to learn and apply. Thank you, and we are now open to questions.
All right, thank you, AI traders. Judges, any questions?
I guess Arnold will have a lot of questions, but I'll just throw a few. Thank you guys for the presentation. I probably missed it from the beginning. Was it? Did you build a global model or a regional one?
Hi, Nikunj here. We built a regional model, and the data is from the Ile-de-France region, and currently it only includes the 8 locations of the wind farms in that region.
Again, it's for France, right? It's
Yes,
northern Atlantic, basically.
No, like even in France, it's just the Ile-de-France region.
Okay,
it's not even all of France, yeah.
Okay, I got it. And how long is the data set? From which years?
2017 January till present.
Okay, I got it. Thank you. So you got some very good results, but some fluctuations on a bigger scale. I guess my effect is just keep it in mind, and probably you would want to have it also incorporated for the longer runs.
Right, yeah. I think the fluctuations are because of the skewness in the energy plot. If you go back to the histogram slides, you can see that the data is very skewed to the left. Like there are more values which are of less production than we have of higher production. And that's why our model certainly underpredicts during those phases. But like Suyash pointed out on the improvement slide, that we have included a loss function that now makes it work slightly better in the overproduction phase.
Okay.
Any other questions from the judges?
Did you guys try discarding the older data?
We did try to discard the 2017 data, and later we made a judgment call and did not deploy it during the competition. But now we think it would have been better if we had discarded the 2017 data altogether, because that data is only for low productions. Like, there are not any values that cross certain threshold, but we saw productions of order of 60,000 during the 10 hours in between on day 4 or day 5. So we do think that excluding the 2017 data and retraining the model on data starting 2018 would give us better results on the production values of the order of above 40K.
So could you explain the judgment call that you made? I mean, why did you choose not to discard it? You had some discussion, obviously.
That was mostly because we couldn't really compare the profits altogether. Since we had excluded the 2017 data, our test set was also lesser. And in AutoCAF, the profits, we couldn't really compare the profits on the face value. So the judgment call was basically that since we're already in the top 5 on the leaderboard, let's trust our model and not deploy it in the middle of this competition. It was really on day 3 or day 4 that we took the judgment call.
If I'd like to add one more point, our objective was to create a stable and consistent model, and we wanted to ensure that there was always constant liquidity. So that's why we wanted to ensure that at any given point, our team was making enough profits, so that there was not a scenario where, in an anomaly where we had less cash in hand.
Okay. And I'm guessing at the last stage where you modified your loss function, you used the MAE as well, but biased it. Is that right? Or did you do something else?
Sorry,
Could you want to answer that?
Yeah.
Yep.
Hello.
Yes,
Okay. So I'm gonna explain our loss function. So it's a weighted MSD. So because when I plotted the data out, I found out that in the last 25th, in the 75th percentile, the data ranges from 25,000 to 89,000. So because of that, we decided to assign a weight of 1.5 to the means the spread loss at that point. And we also assign a weight of 1.5 for every over prediction. We decide because honestly, using MAE would capture the actual loss more, but at the same time, because this competition is used for a short duration, only over a week, and using MAE, it's harder to detect some outliers. So that's why I decided to use MSC with weights. Yes.
Good answer. Thanks.
One last question.
Yeah. So hello, AI traders. Well done. Obviously enjoyed looking through your presentation. One of the questions I had was feature engineering is obviously a big part of your models, right? And in fine tuning as well. So could you explain to me how you arrived at the best feature for the model, and some explanation on that side?
Hello, it's Koi. I'm going to take this question. Because thanks to our EDA, we came up with some basic idea. Firstly is wind direction doesn't help much in prediction because of the low distance correlation of around only 0.2. So because of that, we decided to use fewer inputs for in our prediction, regarding the wind direction data. And apart from that, one main point is when I plotted out the correlation between wind speed data and wind direction data, I didn't see any possible linear correlation between them. That's why we decided to use the product between wind speed and wind direction to capture the non-linearity of the weather forecast.
And to just add to that, since we also saw seasonality in the changes, we decided to include mean, SD, and min and max of the past month of the from the present, just to capture the idea of, or just to get the context to the model that it's this month and the graph of this month should look like that. And since we also saw quarterly changes in the data, we decided that it's best if we have data ranging from the past month. So that's why we have a feature which is basically 0 minus -719. This is like the past 30 days of data, and mean as the min and max of that.
Okay.
The last point to add on is that we decided to use the smooth label because the data is actually pretty noisy. And like when experimenting, we found out that actually smooth label kind of helps in the long run as we achieve like better test loss and better like simulated profit. But then of course we acknowledge the problem with smooth label is because like sometimes it's harder to react to like sudden changes. But I think like as this competition showed that we were consistently in top 8. So I think this approach is one thing to really worth like considering.
Okay, thank you.
Okay, thank you. Okay, before we move on, right? The first step is that like you don't have to thank AI for Impact. It will not affect your results, and I think you can spend your time actually like sharing more useful stuff about your models. So you don't need to thank us, and I think you can thank us later on by taking a picture together. Okay. For the second one is Team Chiwa. Unfortunately, Team Chiwa is not able to hear today because they just started their full-time work. But I do have their videos, so I mean I'll just showcase it for you guys.
Some years ago, I was flying through Newark here.
Through interpolation and last observation carried forward, meaning to copy the most recent available data. It turned out that copying the most recent row was more effective than linear interpolation. Secondly, to ensure that each row of our input has the same number of features, we have removed several rows in front and at the end that does not have a target or enough previous time frame to calculate necessary features such as momentum or force. Another issue we have resolved is the ambiguity in the degree representation of angles. To explain a little more on this, even though the angle difference between 359 and 357 is equivalent to the angle difference between 359 and 1, if we make use of degree angle representation.
Sorry, Christian, is it really going from the beginning? Or are we missing something?
Difference of our final.
Their timing actually exceeds 10 minutes, and the first slide is an introduction about the problem sets. So that's why I didn't show that, because they have to strictly follow 10 minutes regulation.
Okay.
All right.
Cheers.
Prediction. Hence, in order to solve the ambiguity in our angle, instead of using radians or degrees, we have converted the angle into two features, being cosine and sine. We were able to check that this had led to better performance in our prediction. Another change that we have made is to extract month and time from t+0. This is based on our assumption that there is a trend in the wind energy production based on month and hour of the time of our interest. With this extracted month and time, we convert them into one-hot encoding vector forms, which eventually converts time into a vector of size 36, which is a concatenation of month vector size 12 and an hour vector size 24. The reason why we chose one-hot encoding is because if we regard January and February to be 1 and 2 respectively, this implies that the effect of January is twice smaller than February and 12 times smaller than December, and we all know that this is not true. Two other changes that we have made were normalizing our data and changing our target with respect to the time difference with lead time. Since these processes are quite conventional, we will skip this part for the sake of time constraint. Now we will talk about the additional features we have added into the model for better prediction. There are 4 such features in total, which are window mean, window standard deviation, momentum, and force. Window mean and standard deviation can be seen as features representing the sparsity in the window data, which allow models to narrow the range of output values. Similarly, momentum and force, which are the first and second order differences, with the difference being the lead time, can be seen as features representing the gradient and concavity of the graph at the time frame. For this particular problem, the difference will be 18 hours. Therefore, eventually, we can regard this additional features as a way of inputting more information about the recent time frame through sparsity and the information about the graph we aim to predict in the future. To discuss about the final shape of our data being loaded, each target will be predicted based on 435 features. These features are concatenations of the features that we have discussed above. After hyperparameter tuning, we decided 10 to be our window size, and the forecast feature, which is 3, is representing 1 hour's forecast value in one region. Since we make use of 16 region data with 6 time frame, the final forecast feature will be 3 times 8 times 16. Eventually, we split the dataset into train and test dataset with the ratio of 4 to 1, and the validation dataset was derived from the training dataset. With regard to the validation dataset, we have chose the oldest 20% time frame to be our validation dataset because we wanted the training data to be as highly correlated to the test inference, which is to predict t plus 18 based on t plus 0.
Now let's talk about the model. Our neural network model was implemented in Python, and all the training, testing, and deployment processes were fully automated so that we do not have to manually train and test the model every time the data was updated. We used a difference model that updates the weights for the difference between the values after 18 hours and the current value. We use 4 hidden layers with number of nodes 256, 128, 64, and 32 with Adamax optimizer. For the error and loss function, we came up with our own customized loss function and log-cost loss function to penalize more on the shortfall. We'll talk about this later. All the hyperparameters were automatically tuned using the grid search algorithm, which is provided by the scikit-learn library of Python. We have set the learning rate of 0.001, batch size of 16, total epochs of 20, window length of 10, and for every 10 epochs, we decrease the learning rate by multiplying 0.1 to avoid the overfitting. Now, let's talk more about the loss function. At the early stage of the development, we had several options to choose as our loss functions. However, we wanted to train the model in a way that the model avoids the shortfall. Among many, we focus on MSE loss with L2 regularization, our own customized loss function, and log-cost loss function. This is the traditional loss function of L2 regularization with MSE. As mentioned, models with the traditional loss functions do not distinguish when there is a shortfall or not. As shown above, since the loss function squares the difference between the prediction and the actual, the equation ends up having the same sum of the square differences no matter the actual is smaller or bigger than the prediction. To avoid this and let the model avoid the shortfall, we multiplied lambda 1 when there is no shortfall, where lambda 1 is from 0 to 1. By introducing another hyperparameter like this, loss is bigger when there is a shortfall. By keeping the regularization term in here, we expected the model could be more generalized with this loss function as well. However, even with the regularization terms and parallelizing strategy, when there were a lot of outliers with extreme values within the training dataset, the model tends to be largely affected by these outliers. Therefore, we replace the loss function into something that could avoid these outliers. Log cosh is approximately equal to x squared over 2 for small values of x, and similar to absolute value of x minus log of 2 for large values of x. This means that log cosh works mostly like the mean squared error, but by penalizing the extreme values with log, the model is less affected by the outliers, which may lead to shortfall. By leveraging on the property of the loss function that prevents the model from being extremely affected by the large and small values, we expected the model could avoid giving us the values that are always small or always large.
Now, how do we decide which model or functions work best for our use cases? First, we tried to evaluate our train and loss functions to decide the model fit. Second, we designed a loss function and tried out a few others to decide which function performs better. Finally, the mock trading system was used to evaluate the trading result. This is one scenario in which we tried out different loss functions with same parameters. Orange line represent the traditional loss function, whereas the green represent our loss function. However, we observed that the red line, which denotes the log cosh loss function, the predictions of log cosh loss function model produces a smooth graph, which is not heavily affected by outliers in the datasets. The spike in validation loss graph on the right represents the step size decrease in learning rate. The model learns steeply until the first 10 epochs and decreases its learning rate afterwards. These graphs represent our result compared to the ground truth. When designing the customized loss functions, we tried to penalize the predictions that are higher than the ground truth, such that the model would be sensitive to predicting over the ground truth. We ran a mock trading program to test our model's performance. As mentioned before, our final goal is to maximize profit. Hence, the trading result can be different from the loss result. We tried to pick our hyperparameters to target best trading result as well as the training loss. We could observe that our cash in hand keeps increasing as the time passes. Here is our numerical result of RMSE for the test set. Our best model could get 0.8033 test RMSE. Even though we luckily made it to the final and all the pipeline, including data engineering, model implementations, and result analysis seems to be reasonable, there were several limitations. First, we could use external data sources apart from weather data to introduce new features. Moreover, any time imputation strategies may induce different features. Second, we could see that log cosh loss function outperformed all the other loss functions in terms of validation losses. But we believe that more sophisticated loss function may lead to better results. Introducing more generalized or customized loss functions would be more flexible to be modified, providing further rooms for interpretability of the model. Third, our model was not robust enough. We have figured out that even with our efforts to regularize the model seemed to yield a prediction relatively higher than we expected. We believe that this is because at the initial stage of building our model, we had not fully tested the model with various validation datasets and did not modify the model much after the actual trading had started. We could have used AutoML to improve this part so that the model can fix its defects and tune hyperparameters itself. Fourth, we had limited computing power since we were not using the server provided by AI4IMPACT. We could use cloud computing services instead of local computers. Fifth, since we had to update the dataset every UTC hour, we had to deal with the extraordinary forms of data. We had to handle a lot of exceptions to make the automated system robust.
All right. So that's the presentation from Team Chiwa. if you have any questions or would like to connect them, just let me know. Then I can connect with the team. But meanwhile, let's move on to the next group. Group Stongs. Are you ready? Are you ready?
Yep. Just give me a few seconds.
Right. Okay, you can start anytime you like.
Good afternoon, judges and fellow participants. We are Team Stonks and we're presenting our work for the AI competition. For data cleaning, the energy data had minimal gaps that was forward filled. For the forecasted wind direction, ordinary interpolation using mean may not work because we will lose the specific direction of the wind. Hence, we try to calculate the cosine and sine direction before linear interpolation to preserve the wind directionality. However, we found that this worsened our test loss. Hence, we decided to stick to the original naive interpolation method instead. One interesting data cleaning method we did was to set the wind speed of all non-operational farms to 0 to reduce the impact of this non-existent farm on the energy output. And we found that this data cleaning reduces our test loss by 4.8%. The scaler we use for this data set is min-max scaling. Moving on to data analysis, we first plotted a time series of energy production across different time scales, from daily to yearly. While there are peaks and troughs in the graphs, the periodicity of the graph or the data is low. To back this up, we plotted the autocorrelation, and we see that correlation value drops off sharply after 9 hours. The implications of this is that we are able to engineer features to help the model pick up periodic trends. We base our window sizes of this, creating window sizes of no greater than 9 hours. Next, we calculated the correlation between wind speed and direction with energy, and found that wind speed is highly correlated with energy. But we also believe that wind direction has a role to play, even though the correlation value is low. As you can see from this plot here, we can see that even though wind speed is low, there's no clear-cut in speed where energy produced is consistently 0, which suggests that wind direction is somehow influencing the energy output. Furthermore, from the wind rose diagrams on the right, we can see that the wind direction for when energy equals to 0 and non-zero is different. For instance, for wind generally blowing in the northeast-southwest direction, energy production is greater than 0. For winds blowing in the south direction, it's more likely that the energy production will be equal to 0. Next.
Moving on, these are the features we used. We note that taking spatial average of wind speed and direction did not help us. First, we considered 2D cyclical time, which preserves the true distance between time points. However, our experiments showed that 1D sequential time is superior, possibly due to the lack of strong periodicity in wind energy, where 2D time is not helpful in further clustering the data. We also found absolute time to be helpful, counting time from the beginning of the training dataset. Next, we calculated the sine and cosine of wind direction to capture cyclical nature of direction, where 0 and 360 degrees are the same. This is backed by a 10-fold increase in correlation value with energy compared to raw wind directions. Moving on, wind energy theoretically follows a power law and is proportional to cubed wind speed, again supported by the high correlation values shown, and further reduced our test loss. Now for our most important feature, combining wind speed and direction. First, we plotted a scatter plot of wind energy against direction, with the darker spots representing higher wind speeds. We noticed 2 clear clusters, one around 45 degrees and another at 2 to 5 degrees, which usually leads to higher energy. Conversely, the directions of 135 and 315 degrees lead to lower energy production. Therefore, we inferred the ideal wind direction for the turbines and proposed a novel cosine square function multiplied by speed. On the right, we see how our function shows good monotonic relationship with energy and good correlation values, and improved our test loss by 10%, which is by no means trivial.
Can you...
Chris, you're muted.
Chris, your mic.
Guys, we can't hear you.
Is it okay?
We can't hear Chris' mic.
Yeah, it's okay. I can cover for you. Yeah, so for the modeling side of things, we decided to use models that are state of the art in the domain of energy demand forecasting, such as one-dimensional CNN, LSTM, and an architecture that uses a combination of both, as suggested by Tian et al. In 2018. A detailed description can be found in our Medium article and GitHub repo, which is shown here. These figures show how our model performs in the simulated trading and lag correlation. We plot these results with an upper bound, which is the perfect forecast, and a lower bound, which is the persistence. On the left, we see how all the advanced models outperform MLP in trading performance, with the three advanced models being more or less comparable. The lag correlation plot on the right tells the same stories, where the more advanced models can achieve clear lag of 0, while MLP has a clear lag of 18 hours. We attribute this boost in performance to how the CNN and LSTM architectures efficiently filter important sequential information about time series. While this is of course possible to achieve with MLP, by adding more features or more feature engineering, we suspect that the lack of an operation that represents filtering and summarizing of important information might cause MLP models to perform slightly worse or require more parameters. Here we show an illustration of our trading performance. The blue represents true values, while orange represents our predictions. We also realized that the profit structure outlined in this competition is not symmetric, where overprediction is penalized 2 times under prediction of the same amount. We believe that common symmetric losses like MSE and MAE will not be able to reflect this profit structure accurately. Therefore, we propose a different loss function called opportunity loss, which takes the mean difference between the reward given of that all forecasts are perfect and the reward given our predictions. This loss function is flexible enough to represent any log profit structure. On the left, we show how the trading performance of opportunity loss is comparable to MSE and MAE when the profit structure is symmetric. But given an asymmetric profit structure, the opportunity loss clearly outperforms MAE and MSE, not only in terms of average profit, but also in terms of tighter variances. As one might expect, how our loss outperforms MSE and MAE is by having the tendency to underpredict more than overpredict. We note that our model predicts the differences between T plus 18 and T0, which is a less skewed distribution than raw energy values, enabling our model to better handle outliers. For feature selection, we added the features one by one, retaining only the features that improve our test loss. We conducted sufficient repeats to reduce the variance from random weight initialization. This approach assumes minimal feature interaction, and therefore we tested certain feature combinations based on intuition. Using freely available GPUs on Google Colab, the model training is very fast and takes less than 40 seconds. After finalizing our best features, we did a random but controlled hyperparameter search. Moving on to our results, the scatter plot of differences is noticeably tighter than that of raw energy, but both show very good one-to-one relationship. Also, our model underpredicts as intended as compared to MSE loss on the right. Lastly, our peak lag is clear 0. Next, our mean loss beats persistence by 77%. Most importantly, our revenue beats persistence by 131-fold and is 64% the maximum revenue, and is clearly superior to both MSE and MAE losses. Moving on to deployment, a critical mistake we made initially was training on the entire data set without any test set, having no idea we had a bad random initialization, which made us miss the initial peaks and lost some money. On top of having a test set before deployment, we also took the average of LSTM CNN and 1D CNN model predictions to get more stable predictions with tighter variances. Our deployment is also fast and simple, taking at most 25 seconds. Once we fixed our initial mistake, we were more or less first on the leaderboard throughout the competition, 13.8% above the average of the other 9 teams. Here an example of how we captured the first major peak well without over-predicting. We note that in the short term, MLP is comparable to CNN and LSTM, resulting in the tight competition. But in the long term, the advantage widens, as shown on the bottom right. We also floored our predictions to 5,000 for July, an insight we obtained during our data analysis. Moving on to limitations, this includes the lack of obvious patterns in the data, which made feature engineering difficult. For example, we found the exact model of turbines in Innovate, France, and found their cut-in wind speed, but using that did not improve our test loss. We also recognized the importance of maintenance hours. However, we were unable to infer this from the data. Lastly, we would have loved to use more weather data like temperature, humidity, and storm alerts, but could not obtain this data under time constraints. As for improvements, firstly, our model might be too conservative sometimes. To overcome this, we experimented with different opportunity loss ratios to encourage more daring predictions, but did not obtain conclusive results. Something we can try is to blend models that underpredict with those that overpredict and find the sweet spot. Secondly, we can consider more complex weather effects. For example, the height of wind speed forecasts do not match the height of the turbines. So correcting this using physics could help. Lastly, rainfall is possibly important as it increases drag and decreases the turbine performance. In conclusion, these are the steps we took, and thank you for listening.
Any questions, judges?
Thank you. Maybe I can ask a question.
Sure.
Thank you, guys. So I have a quick question about the short-term predictions, and maybe you have seen that also for wind production forecast right now, the output forecasts for, like, say, 5 to 30 minutes ahead predictions is also becoming very important. And I just noticed that you don't have a constant results for it throughout the peaks. Do you have any comments on that? Although the overall results, they look pretty good. So again, my question is about the short-term ahead energy production forecast.
I think in terms of consistency, it wasn't that our model was inconsistent, but rather that we made an initial mistake where we thought that by training on the entire data set, we could improve the predictions just a bit more. But when we did that, we ran into a sort of an unlucky situation where our model was had a bad random initialization. But we didn't know because we trained on the entire data set and had no test loss indication. So once we realized this, about a day into the competition, we quickly changed to the initial setup where we train on 80% and we test on 10%. And from then onwards, we're able to consistently maintain a first place. Yeah, so going on to short-term predictions, I believe our model should be able to handle that pretty fair, because currently it's predicting 18 hours ahead and it's still able to capture all the peaks and troughs. So I assume that for nearer time spans, it would be even better in predicting the trend. Yeah. Jiang, do you have anything to add, or Chris?
I think it's good.
Okay.
I have a couple of questions. So just a follow-up question on that, on what Misha asked you guys.
Yeah.
That is that for the initial time when you did the training over the entire data set, what was the sorting criteria? How do you know when the model is being trained enough? How do you know if it's being overtrained? What's your sorting criteria?
Yeah, so from our extensive hyperparameter search, we know that what is the average number of epochs needed for this set of hyperparameters. So we found that there was about 7 epochs, and yeah, we even did we even checked that multiple times and made sure that we were not running into this. But yeah, unfortunately, we realized that there is significant model variance if we don't check the test losses. Yeah.
Okay. One other question is that early on you mentioned that you use absolute time as an input. Could you explain that a bit more?
Yeah, so this is basically for the first row of our data set, the value of this feature would be 0. And as we proceed down the rows, it would increase by 1 every row. And so our test data would have the highest values. And this would be scaled by min-max. So we found that this improves the test loss by up to 5%, which wasn't very intuitive to us, but we thought that maybe it could be in how 1D-CNN or LSTM handles the data better if we give it some indication of the sequence.
But the whole point of it, it can remember what's happened in the past, right? And why do you think giving a monotonic sequence of numbers would improve performance? Is it something that's real? My point is it something that's real, or something that is just accidental due to your training regime or something else?
I can take this. Yeah, the reason behind this is to include kind of like something that will capture the absolute kind of like the trend in absolute time, the general global trend instead of like a more local periodic trend. So I think like that's the rationale behind this. Yeah, and to answer the question more directly, we were not too sure whether like it's because of the interaction within the model or because of like the feature engineering. But it seems that like the experiments shows that, yeah, it improved our test loss. Yeah.
One last question.
Yeah, can I just ask a question on there was a slide where you guys detected that removing the non-operational plants improved your error loss. So how did you spot this? Was this a lot of trial and error before you came up with this, or how did you spot this through your data visualization, or how did this come about?
I'll take that question. So initially, the main trouble we have with this data set is that the energy given to us is the aggregate of all 8 farms, and the 8 farms are not all operational at the same time. So it was difficult to isolate the contribution from each farm to the total energy output. And then one way we thought of maybe that it will work to reduce the input from like a non-existent farm was to set it to 0. And so we just did like rigorous testing, like removing the feature and putting it back in, and we found that it does improve our test result. And yeah, so we decided to keep it in. I think it's setting it to 0 allows us to better isolate the signal from operational farms.
Yeah. Okay, thank you.
Okay, thank you, judges and Stongs. Thank you so much.
Thank
you. Yeah, so next team will be Team Maverick. Please get your slides ready. And just to share some best practices from Team Stong is that like whenever the judge asks question about particular slides, right, or particular presentations, try to actually navigate your slides to the question to where the relevant content basically. Okay, thank you guys. You can start now.
All right, let me just check. Can you guys see and hear me?
Yeah.
Okay, thank you. Okay, hi guys, I'm Lakal, representing the best team, Team Maverick, in our presentation of our approach to wind energy forecasting. And even though we had 0 experience in AI, we are still here to blow away our competition. Okay, so what we're covering today, we'll go through our introduction, our data analysis, our persistence error, our inputs, and our network configuration. Then we'll cover some of our pre-deployment results, our issues faced during deployment, and lastly, our deployed results. So firstly, our problem statement is as follows. We are to perform the role of an energy trader, where we have to predict the expected production of wind energy produced by wind farms. Our role will help maximize the profits of wind energy producers by reducing excesses and shortfalls. And this will eventually help France achieve its 2022 goal of doubling the energy output from 2017. As an energy trader, we are tasked to make T plus 18-hour forecast predictions of energy output, and we are compensated 10 cents per kilowatt hour. And in case of over forecast, we have to purchase energy from the grid at 20 cents per kilowatt hour. And in the case of under forecasting, we only profit from what we forecasted, and it results in energy wasted. So come to our data analysis. We have 2 sets, wind data and energy data. So firstly, for wind data, we are given 2 wind models at 8 locations in Ile-de-France regions, plotted on the map on the right-hand side, and 2 variables, wind speed and direction, and they are all interpolated to 1 hour. These locations are subjected to slightly different wind conditions because of their distance and proximity, but are affected by similar regional seasonal trends. For energy data, this is real-time data of interval of 30 minutes, but aggregated to 1 hour. The data given is within the time range of January 2017 and July 2020, and we have 2 options for normalization, min-max and standard score. But however, we consider that all data points be important, and since standard score reduces the significance of outliers, we concluded by using min-max normalization. In the long run, we also observe an increase in energy output over time, and we attribute this to an increase in number of operating farms. So, most recently, we have Angerville wind farms deployed in July 2019. Thus, from July 2019 onwards, we see that there is a presence of 1 full year of complete data. So in our model training, we simply use input data from 2nd July 2019 onwards. Now in these 3 graphs, we sampled data of energy output of 14 days from 3 different windows. And so we note that there is a pattern in the daily energy output, where energy output rises to an intraday max or falling to the minimum. The rate of fall or rise varies, and this pattern is not constrained by a 24-hour window, but is close. So we choose to use the following feature inputs to help us leverage on these data trends: 24-hour min-max, 1 hour difference, and moving average. Now coming to wind speed, we first note the limitations of wind turbines. We have cut-in speed of 2 to 3.5 meter per second, or a rated speed of 12 to 14 meter per second. What this means is that any wind speed below 2 meter per second will not register energy output, and any wind speed above 40 meter per second will not result in an increase in energy output. And from the data summary on the right, you see that there is a distribution of wind data because of the lower quartile and a max speed falling within the cut-in and rated speed. We were not too concerned about these limitations. I bring our attention to graph C. We plotted a graph of energy output against wind speed, and we calculated a correlation coefficient of 0.94, pretty high. So since wind speed is highly linearly correlated with energy output, therefore, we saw that wind speed is a good factor to help us predict energy output. For wind direction, firstly, we need to note the effect of wind direction on wind turbines. Because wind turbines perform yawing when wind direction changes, the high variability in wind direction would result in a reduction of energy output. So you see in this plotted graph of energy output against wind direction variance, we see that wind direction is slightly inversely correlated with energy output. So we used a difference calculation given by the formula that you can see in the annotations box on the right. So to summarize our inputs, we use wind and energy data from 2nd July 2019 onwards, energy output with the following features: wind speed from all 8 farms at T plus 18 hours, and wind direction difference between T plus 18 and T plus 17 for each farm. We derived at 0.207 persistence error, the error that we have to beat. This graphics here helps us easily visualize our model. From the left to right, the input is first clamped before we feed it into an autoencoder of bottleneck size 8. It is then fed into a feed-forward network of neural network size 1 to 8, and decreasing in factors you can see in the graph. All perceptrons have 10 head saturators. We have dropouts of 0.165, ethers of 10,000, and solver type atom. So pre-deployment, we achieve a test loss of 0.01, beating the persistence of 0.207. We achieve moderately strong correlations between actual versus test predictions, and we minimize lag to 0. Now comes the crucial moment, deployment. So firstly, we face some problems with regards to wind direction data. Firstly, because of the distribution of several major peaks, we thought it was difficult to apply transformations or standard score normalization. So instead, we relied on feature engineering for more helpful prediction of the data, and we use difference calculation rather than raw data. Now, we also acknowledge the cost of over-forecasting being 2 times the cost of under-forecasting. And this hurt us greatly on day 3, where abnormally low energy output resulted in a spike of losses. So we worked quickly and we observed the trends in wind energy output, and then we tried to scale down our forecast by a magnitude of 20%. We acknowledge our solution is not perfect though, as it creates an incentive to under-forecast, which is harmful because it results in higher wastage of energy. So instead, we thought we could have implemented a loss function which is biased against over-forecasting which could be achieved by assigning different weights to bias the loss calculation through creative use of ReLU, which would be a more precise way of reducing over-forecasting. We also noted early on that our test loss did not reflect our deployment loss, and we were reminded that our wind energy is seasonal. Therefore, we retrained our model very quickly using recent data from 1st June 2020 onwards. To bring it one step further, we could improve the accuracy of our forecast if we had the energy output data for each farm, as we recognize that each farm output is weighted differently and experiences different wind conditions. Analyzing our deployment results, we also noted that the predictions are more influenced by historical energy output instead of wind forecast. So given the opportunity, we would retrain our model by prioritizing the inclusion of wind data. At the end of the day, we managed to achieve profits of 1.4 million cents. However, we also wasted 23.84% of our energy and achieved only 49.58% of our maximum profits, and that is reflected in our t-test score of 0.177. However, we are optimistic that our results can be improved, and we believe that through the implementation of our proposed solutions in the previous slides, we can definitely become better energy traders. Thank you. Now we open ourselves to Q&A.
Judges?
Thank you, guys. So as you mentioned in the end that the inclusion of the more data really helped you to improve the results. Why did you not include the more data even from the past that you had?
Okay, so I guess the first question we question ourselves was why did we use energy output? And it was because we wanted to use data trends to kind of predict our forecast, because we noticed that wind direction and wind speed previously did not give us a full picture. So for instance, like low wind speed will still have a wind energy output. And then because wind energy output follows a regular pattern, so we kind of had the idea of using wind energy output. But given a chance, we would have use wind speed and wind direction data more.
Any other questions from the judges? One, two, 2.5, 2.75, 2.9.
One last question.
Oh, okay. Okay.
So just to clarify, your inputs were what kind of inputs do you give the model? So it's just these few inputs, nothing else.
Yeah.
Wind speeds, wind directions, and the energy max and min over the last 24 hours. Is that right?
Yeah, including the average and 24-hour 1 hour difference for energy output.
Okay. How do you decide on a 2nd July 2019 cutoff? Why this magic date?
Because of this reason, the increase in number of operating wind farms.
Okay.
So 2nd July 2019 was when there was an inclusion of all the 8 wind farms.
Right. Right. Okay. And one last question. You said you use MAE, is that right, for your loss function, or do you do something else?
No, we use a standard RMSE.
Use RMSE.
Yeah.
Okay. But your losses, you're penalized for over forecasting, right? More than for under forecasting. How did you incorporate that effect into your models?
So we thought like if given a chance, we would try to implement like the bias loss function.
Okay.
However, he didn't really know how to do that. So instead, we tried to scale down our forecast magnitude instead. Yeah.
Okay, so in other words, you just scale it down.
Yeah.
Okay.
Yeah.
An issue we face with scaling down the model is that during times where there was a very high actual output, we actually lost out on quite a lot of potential money. But in exchange, we actually lost less money when it was like around the low periods of energy output. So I think in overall, we actually benefited from scaling down by 20%.
Okay. Okay. Thanks.
Yeah.
That's all for me.
Any other questions? Okay. So thank you so much, Team Maverick. You can disable the screen share now.
Okay.
Next
thank
one
you.
is Deep Sleep. Deep Sleep, are you ready?
Yes. Yep. Just.
Okay, all your members are here.
Yeah.
Okay. Good luck. Good luck.
Yeah, just pull up the slides.
Chris, maybe between teams, you can give us, let's say, about 30 seconds just to put in the mouse or something.
All right. Sure. Maybe I just fill in for now. You guys can. Okay. Deep Sleep. Also, please practice social distancing.
Oh yes. We should wear some masks too.
Yeah. So okay.
We're just having a bit. We're just trying to find which one is the right.
For some reason, our screen share is not showing.
I've disabled. I've enabled to all to do.
Again.
It's a green button.
Yep. Just give. Okay, just 1 second. I think. Yeah, I think it should be fine now. Okay. Sorry, it was a computer problem. Oh, there we go. Okay, apparently we need to leave to be able to share our screen for some reason.
Can you share your screen right now?
Yeah, let's just. Oh, okay.
Oh, yeah,
Oh, yes. Okay, actually it worked.
Yeah, sorry
Can you see it now?
Yes.
Does it work? Okay, perfect. All right. Sorry for the delay. Good afternoon, everyone. We're Team Deep Sleep. My name is Tianwei, and I'll be presenting together with my fellow teammates, Cleon and Isabel. Today, we'll be going through what the challenge is, how we handled the data, the journey to our final model, and certain limitations that we faced and how to improve on them in the future. So the biggest challenge to forecasting wind energy is that it's highly dependent on environmental factors, such as wind speed and direction, where variance at a granular level tends to be quite high. As established, our role as the energy trader is to help the wind energy producer to maximize their profits when selling the energy to the grid. We do this by producing forecasts on behalf of the wind energy producer. If we under forecast, we lose 10 cents per kilowatt hour in potential profits. And if we over forecast, every kilowatt per hour over predicted is 20 cents lost in revenue. From this, we know that our model should not be penalizing over and under predictions to the same extent. So to approach how we handled the data, we were given two data sets, hourly wind energy production levels in France from 1st January 2017 to present, and wind speed and direction forecasts from two sources for 8 locations in the Île-de-France region, each of which represent a major wind farm in the region. What we observed is that wind energy supply is highly seasonal, with more energy being produced during winter and autumn and less in the spring and summer. There is also a gradual uptrend of energy being produced over the years, which could be due to improvements in technology or an increase in the number of wind turbines in the region. On a more granular scale, we took an average of wind energy production every hour since 2017 and found that wind energy production peaks at around midnight and troughs at around 8 a.m. We also found that in the second data set with the 8 wind farms, there is little variation within each model's forecast of wind energy production. However, the forecasts from both models A and B differ significantly. This later informs our data pre-processing. Another interesting observation we made with this wind rows chart is that in both models, wind generally tends to blow northwest and southeast. Through our preliminary data analysis, we were able to make better decisions when pre-processing the data. When pre-processing wind speed, we took the observation that there is little variation within each model's forecasts and spatially averaged the data from the 8 wind farms. We also did not combine the two models since they differed significantly. Then we normalized it. For wind direction, we had to treat it differently because it isn't accurate to just average the data. Taking the average between 359 degrees and 1 degree will give us an average of 180 degrees, which is the complete opposite direction. Therefore, we converted degrees to radians and chose to normalize them using sine and cosine to ensure that they have a rough magnitude of 1. We then spatially averaged the normalized directions separately for each model. By doing this, we managed to cut down the number of columns from 33 to 7 without losing much information from the original data.
Now we will introduce the models that we ran. Before moving on to building our models, let me first introduce the two metrics we use to judge our models. The test loss based on the MAE loss function and the actualized profits to total available profits ratio. The persistence benchmark to beat is around 0.65 as shown. We first ran model V0 to be used as our baseline model. It takes in the value of wind energy at T0 and the three averaged values of the T18 forecasts of wind speed and wind directions per model, resulting in a total of 7 basic inputs. The model achieved a test loss of 0.73, which did not beat persistence. The model also earned 42% of the total profits available to be earned in the test period. We see in the upper left diagram that the test loss remains very high, indicating the model is not generalizing well. In the test predictions graph on the bottom left, we see many red spikes at the bottom and exposed blue spikes at the top, an indication that our model is often underpredicting. We can also see this from the actual versus test predictions graph on the top right. On the bottom right, we have the lag correlation graph, and we see that the test peaks at 1 with a secondary peak at around 18, which is not ideal as we want the model to peak at 0 to be useful. Thus, we perform feature engineering. This table shows the best performing set of features we engineered with the respective windows used. During the iterative feature engineering process, we experimented with a wide variety of features. Two interesting features that we thought intuitively would be useful but did not turn out so were cubic values of wind speed and the interactions between wind speed and direction. Cubic wind speed was inspired by the wind power generation equation, where wind speed enters the equation as a cubic term. The interaction between wind speeds and directions was based on intuition. We suspected that wind blowing at high speeds in the wrong direction or wind blowing in the right direction but at low speeds were both not useful for generating wind energy. However, these two features did not end up improving our models based on the two metrics. Next, we ran model V1, which is similar to model V0 but using our best set of features. Both test loss and profit ratios significantly improved, and we are now beating persistence. However, from the top left graph, we see that test losses still remain high. On the test predictions graph on the bottom left, while there are lesser red spikes at the bottom, there are still many blue spikes at the upper region, indicating underprediction of higher values. The good news is that from the lag correlation graph, we see that we have managed to achieve a peak of 0. To further improve our test loss and profits, we experimented with more network features in V2. The best model we found was similar to V1, but with added 10% dropouts and L2 regularization with a weight decay of 0.001 and input scaling. These changes brought some further improvements to our test loss and profit ratio. While this model helped reduce some of the test loss and the area of the blue spikes region, the gap still remains between training and test loss, and the blue upper region is still quite visible. Our lag continues to peak at 0. In summary, V2, with our engineered features and model refinements, performed the best with a test loss of 0.4794 that beat persistence and the highest profit ratio of 59%.
Now, despite these improvements, there still are limitations to our final model that we deployed that we feel are important to understand. Right, firstly, the test loss is still very high, and the gap between the training and the test losses is still large. Now, this indicates that while the model can learn patterns from the data, it is unable to use these learnings to generalize well on unseen data. Now, we feel that this might be due to noisy training data, or that the data is not truly predictive of wind energy. As such, a possible future improvement could be to source for more predictive data, such as air density and the efficiency factor of wind farms, which are factors that belong to the wind power generation equation that we introduced earlier. Now, the second limitation is the consistent underpredictions that our model generates. We see that the underpredictions for high energy levels are still prominent. This might be due to the varying start dates of the wind farms, thus introducing artificial noise to the data and then making learning difficult. Now, we tried to solve this using weighted transformations or truncated sections of the dataset. However, the original dataset still gave the highest profit ratio. Now, finally, the MAE test loss does not reflect the asymmetric penalization of our profits in the setup. We tried implementing a custom asymmetric loss function that we feel more accurately reflects the profit maximization equation as shown in the slide. However, after experimenting between two loss functions, the MAE still gave the highest profit ratio. This might be due to the fact that our model was already under-predicting a large amount of the wind energy levels. Although having an asymmetric loss function that heavily penalizes over-prediction may have resulted in less over-predictions, it might have caused even more under-predictions, ultimately resulting in a lower profit ratio than the regular MAE. Now, thank you for your attention, and we hope that you enjoyed our presentation. Feel free to refer to our Medium article for more details.
Any questions from the judges? Thank you, Deep Sleep.
Can I just sort of ask the first question? So can you guys scroll to your first limitation, please?
Yes.
You mentioned that there was a high test loss, and you identified that you had less data to work on, so you couldn't bring the test loss down, right?
Yep.
Yeah.
So I mean, what would be the other ways, like practically within this competition? Like, did you guys try to scrape the data from the internet or get some other data source which you could find on a similar region or the same region from the internet?
Okay, so what are some other data that we tried looking for include, for instance, the length of the wind turbines, the air density in like the specific regions, and the efficiency factor of the wind farms. But even though we tried our best to search for it, it seems that a lot of the data on the wind farms, especially, are not very readily available on the internet. So in the end, we did not end up using external data for this competition.
Okay, thank you.
Thank you.
I have a question. You mentioned early on that you tried to use a power 3 of the wind speed.
Yeah.
And you found that didn't give you better results, right? So did you normalize it before you put into the model, or did you use a power 3 of the wind speed, as it is, or did you pre-normalize the wind speed until the power of 3?
What we did was, in our pre-processing and the data extraction, we extracted the wind speed and multiplied it and we cubed it, and then after that we normalized it. So we normalized it after cubing it.
Okay, one question for me is, did you see the increase in over predicting between V1 and V2? It looks like a bit from the graphs that you show. And if yes, then what do you think you can do in order to keep it still under control while increase the, or rather reduce the under predicting too?
Yeah, okay, so first let's take a look at V1. So note the relative sizes of the blue region on the bottom left graph and how the data tends to be below the 45-degree line on the top right graph. Then now we take a look at V2. So it is more centered around the 45-degree line, and there seems to be a smaller area of the blue region above. So what we saw this as was, in V1, we were actually under-predicting quite a bit. And in V2, when we fine-tuned the model, it ended up under-predicting less so. And although it over-predicted a slightly greater proportion of data points, the overall total profits ratio that we managed to achieve was higher, because we were able to capture more of the higher wind energy production actuals when compared to what we forecast. So we felt that this is an improvement to our model.
Thank you.
Any other questions from the judges? One, two. Okay, so thank you so much, Deep Sleep, for your presentations. we still have time. So maybe for now, since we're already halfway there, so we can have a 1 minute toilet break, especially for the judges who already judging 5 teams, intense teams. So
Are you implying that we're so old that we need it really more than anyone else?
I always think that deep learning practitioners are some of special people with a special, because you guys don't sleep, right? Yeah. So okay, maybe in that case, then if 1 minute is not enough, we can just have 2 minutes as well. But meanwhile, you can also take your time also to just relook at your scores as well. But no one is moving. It's just showcasing that you guys are superpowered. And in that case, proving my point, right? Okay. So meanwhile, I think the next team is solo leveling, right? Please get your slides ready and share your slides as well.
Okay.
So yeah. So out of the top 10, just a fun fact: solo leveling is the only solo player here, but they managed to get rank 4. So see what you got. Judges, are you ready? Okay, so in that case, we can start now.
Is it already showing my?
Yes.
Okay. Okay. Hello, I'm from solo leveling team. Oh wait. Okay. So we already know the background and objective, right? So I will just move on to the data sets. So there are 2 main data sets that we will be using: the wind energy production and wind forecast. And both are taken from January 1st, 2017 until present time. So for the wind forecast are divided into 2, which are wind speed and wind direction. And there are 16 forecasts in all because it's from 8 locations, represent a major wind farm in France. And all of them are already interpolated to time base of an hour. So the first thing that we need to do is to fuse our data, because the data sets are divided into 17 that we know, one of energy and 16 wind forecasts. So we need to fuse them into one data set. Therefore, we will fuse the extracted database into one database with 3 columns, which are energy produced, the average of wind speed from all 8 locations, and the average of wind direction from all locations every hour. And the next step is the data pre-processing. This is what I use to normalize my data, that the code above. So basically, I just use data, the subtraction of the data and the mean divided by its standard deviation. So that's all for my pre-processing. I normalize the data with that formula. And the next step is the data windowing and features engineering. So for the features, actually, I use the mean, difference, and max and standard deviation value of the energy from period t+1 to t-18, which is 18 hours into the past, and value of the forecasted wind speed at t plus 0 and t plus 18. The mean value of forecasted wind speed from period t plus 18 to t plus 0, and the maximum value of forecasted wind speed from period t plus 18 to t plus 0, the difference of forecasted wind speed from period t plus 18 to t minus 18, and the values of forecasted wind direction at t plus 0 and t plus 18, and the difference of forecasted wind direction from period t plus 8 and t plus t minus 18, and the spatial average of forecasted wind direction from period t plus 18 to t plus 0. So the idea of using the mean difference max and standard deviation value of the energy from the energy generated is to learn the pattern and possibility of having a spike of energy at a certain time. The use of difference is to reduce the lag, as it's useful and usually gives better results for time series data. And the idea of using the wind forecast data is to take into account the element of wind condition to the wind energy at a certain time, and to know the condition of wind that is blowing in a day as a whole to predict whether it will give a spike of increasing or decreasing energy. And we also use the data from period t plus 18 to t minus 18 for the difference of the wind speed and wind direction, because I want to better understand the pattern of change from the wind condition, because it will not change abruptly. And the next is my configuration. So I totally use this configuration. This is my best configuration that I present here. I use a dropout of 0.1, bottleneck of 10, and I use neural network size of 128 and 256 with Adam solver type. And I also use the autoencoder and input scaling in order to get the current best result. The autoencoder is used because it is good for a large input dimension, and input scaling actually gave me a better result than not using it. And I didn't use clamping because I didn't see its need to use for our case. And for the neural network model, I used a 4-layer network that will run after the autoencoder and input scaling. I use dropouts in every layer and a decreasing number of perceptron for every layer by 2/3 of its previous layer. And the activation that we used is ReLU, and with one inner product with one output. Oh, and for the autoencoder, I use 10H, not ReLU, because it actually gives me better result than using ReLU by my observation. And we also use a wave decay and regularization, which have proven their function by giving me better result than not using them. And we use 0.0001 as our wave decay and L2 as our regularization type. So this is the graph of mining and test losses iteration. And yeah, as we can see from the graph that our model definitely can improve further. And from 25 repeats that we have done to ensure that our configuration is consistent and we get the best result, the test losses is as we can see in the red circle here, and it has already beaten our benchmark, our MAE benchmark, which is 0.64. And we run this configuration. There's our current best result to get the prediction result as shown here. And this is my training prediction and test prediction. And we can see that our spike is not perfect. However, it is not a bad spike, as we didn't get any nasty spike, both at the bottom or above. And it shows that our model can predict novel data, and at least it's not memorizing. And this is the plot of my test prediction. And yeah, it's not perfect and can be improved further. However, we can see that we got a linear shape plot, which means that our approach is on the right track and we were moving in the right direction. And this is my lag correlation. And actually, my lag correlation for the test is I got a peak of 1 for the test. And it's not perfect because we want to have a 0 peak of the test. However, this is my result by the end of my trial and error, and I still haven't gotten the 0 peak for the test in the lag correlation. And for the final profit from the provided data, it is not the live data, is as you can see here. And yeah, the final result is here. And overall, I think that with my current understanding that I got a quite good and satisfying result. One thing is that I didn't end up in a minus profit, even though it wasn't high, but we still got some profit. And this shows that we're on the right track, and this model can still be improved even further to get better results. And for my observation and guesses, I believe that using a much better comprehensive input features and more suitable normalization method can bring me a better prediction model, as I don't have the knowledge with my current understanding today, but yeah, the data of the wind forecast are tricky, as we have to handle the wind direction, which consists of degrees and such. But yeah, nevertheless, I've developed neural network models capable of predicting the wind energy production. So that's all for my presentation. Thank you.
Thank you, Solo Leveling. Any question, judges?
Yeah. Thank you, Anton. Why do you think your model overpredicts in the beginning and then starts showing more stable results and basically move towards underpredicting more than overpredicting? So what is happening in the model in the beginning?
Yeah, so I think that my I don't quite grasp the features engineer and the normalization quite well enough. So the data might be noisy or something that it makes the test losses is by have quite a large margin compared to the train loss.
Okay, thank you.
Any other question from the judges?
Yeah, I have one. So just to clarify, you have got 3 inputs into your model, is that right? Because you use the average of wind speed, well, you've got the historical energy values, you've got the average of wind speed across all stations, is that right? So you got columns A, B, and C, and that's about it.
Yes.
Right? And you did some pre-processing on these to create some features, and then you pass that onto your model, is that right?
Yes.
Okay. Did you try actually separating out the winds and the wind speeds separately, or is this the best? Why did you? What made you want to average across the stations?
As the average because by my understanding, I think that for the wind direction, I just think that the average of every hour in all location can be useful for the model to be trained, because the energy that we got are the accumulation of all of the location. So I just think that the average of the wind direction as a whole in every hour can help to predict the energy.
Okay, thanks.
Any other questions from the judges? Okay. 1, 2. Okay, so thank you so much, Solo Leveling.
Thank you.
Yeah, you can disable your screen share. Next one is Team Anyhow Bomb. So Team Anyhow Bomb, please get your slides ready. And enable your mic as well.
Hello, is my audio okay?
Yes. You can start
okay,
now.
So good afternoon, everyone. I'm Ziguang. I'm joined by Weipin, Derek, and Jiale, and we are Team Anyhow Bomb. And this is our presentation for Deep Learning Datathon 2020. So the problem with wind energy production is the instability of production throughout the year. And an accurate forecast of production will help maximize the energy sold, as well as hedge against the low supply periods to prevent outages. For this challenge, we are taking the role of an energy trader to forecast energy output in Ile-de-France at T+18 hours every hour. From the conditions shown below, we can see that we are penalized more for over predictions. So our goal is to maximize profits, which makes us prioritize avoiding entering debt, as well as reduce buying from the market due to over predictions, as well as reduce wasting earnings due to under predictions. So our plan moving forward was to have problem and data analysis first, and then we move on to data and feature engineering, whereby we test and benchmark consistently and constantly until we feel comfortable before moving on to the network parameters, where we do the same. The measure by which we test and benchmark is mainly due to empirical testing. So what affects wind energy production? Our team looked towards Betts' law, which tells us the maximum theoretical wind power output of a turbine, regardless of the build of the turbine. And we can see that wind speed is most likely the most important factor for this, because it has a cubic factor, whereby air density will rarely go to 0 or to high extremes. Effective area acted on the wind turbine can be 0 if wind direction is perpendicular to turbine, so we will look at that as well. So for data analysis, we were provided with energy production, wind speed, and wind direction of the 8 major wind farms. So we decided to plot energy versus time, and we noticed that there was a seasonal trend whereby energy peaks at the start and the end of the year respectively. So because of our look into Betts' law, we decided to also plot wind speed versus energy versus wind speed, and then we noticed that there's a cubic relationship. We then proceeded to plot energy and speed versus direction, whereby we noticed that there was a very strong correlation for the northeast and southwest winds. And then we decided to look at the geographical locations of the farms themselves and noticed that there are 4 distinct clusters that we could group the wind farms into. So now we established the base networks and benchmarks. We decided to use the normalization formula here, and we decided that normalization is important for our project because energy and speed and wind speeds have different units, and we should make them have the same size to prevent the large values from dominating learning from the model. For our wind direction as well, we decided that because the bearings are in degrees, which are cyclical, and 1 degree is almost the same as 360 degrees from our understanding, but to the model, it might treat it as 360 times more important, which is not the case. So we assigned a unique sine and cosine value pairing to each bearing, so the model will treat it as a categorical data instead. So this is our base neural network, where we took train test split of 7:3, as well as a 2-layer MLP difference network. And for our benchmarks, we compare the RMSE persistence to our test loss, as well as looking at the trading simulation profits. From here on out, empirical testing begins. We will first look at why did we test what we did and what was the best, as well as the results of the best. So we look towards interpolation methods because the wind data is provided 6 hourly. So the intermediate values, we tried to look into other interpolation other than linear interpolation. We also tried a spatial average of 8 farms, as well as wind speeds. We tried clipping, cubing, and squaring. For clipping, we looked and we noticed that from the graph past 10 meters per second wind speed, the values start to deviate from the cubic relationship. However, right, we tried cubing and squaring, but that also didn't perform as well. We suspect it might be because that the model could learn non-linear relationships. We also tried to scale energy and speed to lower ranges, but it did not perform. So the best data processing method that we ended up with was a linear interpolation of wind data hourly, as well as 8 farms to 4 clusters that we observed previously. And then we averaged the wind data of each cluster. For normalization, we stuck to the original methods shown previously without any form of scaling. So we experimented with window sizes, intervals, and for window size specifically, we tried to include the seasonal trends into our features, but it did not perform as well. We also looked into momentum and force, statistical features, wind data further than T+18. However, we ended up on these features because of extensive empirical testing of t+0 to t-54 with an 18-hour difference interval, as well as t+0 to t-36 hours of just raw energy data. For wind speed and direction, we decided to take t+24 to t-54 hours every 6-hour raw intervals for a total of 244 inputs. For our network parameters, we looked into network size, layers, activation functions, Reg decay dropout, input scaling, dimension reduction, and squared perceptrons. We also tried our own custom loss function, which adds a factor if the predicted was higher than actual. But through testing, we found out that it performed worse than the RMSE loss function, so we stuck with that. So this is the best network parameters we ended up with after our empirical testing of an activation function of 0.01 leaky ReLU, dropout prop of 0.1, a Reg decay of 0.0001, and as I mentioned earlier, the RMSE loss function. We also decided on a train test split of 90% to 10% because we realized that this would maximize the training data to around 20 times the actual deployment time. This is our denormalization features. And we did this to prevent ourselves from entering debt and subsequently buying from the market. And we also noted that earlier that it was more beneficial to underpredict than overpredict. So we made our model favor underprediction. So these are the results of our model with a mean test loss of 0.156970, which beat persistence by 66%. And on the graph on the right, we can see that the model is learning well as the prediction follows the actual trends. Next, the lag correlation graph with a clear peak at t+0. So our training simulation was simulated across 3,118 hours on the test set, which hit a 709 potential maximum profit. However, we only achieved 404 million cents, which is about 57% of maximum, which we would expect to perform the same on the live. During live training, we noticed that after the first day, our model was underpredicting way too much for the lower energy values. So we decided to set a minimum of 5,000 kilowatt hour minimum, and we also fine-tuned our denormalization function. On the whole, our simulation hit 57% of max profit, and our live trading hit 53% of maximum. We will argue that this performs as intended. We also noticed that we were consistently in the top ranks of the live leaderboard at this point, so we didn't make any further changes, although there was much room for improvement because of the 40+% profits wasted. Now moving on to the limitations of our model. Our model favored underprediction, which limits the profits and wastes energy, which is very bad for the energy supply chain. And it's also very specific to trading scenario in France. And this can really only be improved through the accuracy of our forecasts. Secondly, the wind data is provided in 6-hour intervals, but we have to predict every hourly, which makes uncertain for intermediate hours, as well as noise during training. We should look to improve interpolation methods by including other wind models. Thirdly, the wind forecasts are also predictions as well, and there will be inherent errors and also that the altitude forecasted is not the same as the altitude at the wind turbines, so it might have some discrepancy there. We should look to combine multiple wind models and maybe transform the wind data using fluid dynamics. Lastly, our model is highly reliant on historical data, which might lead to overfitting and reduced generalization. And the only predictive data is the wind forecast. Prediction quality is also limited by causal strength of inputs. We should look to include more predictive inputs such as air density and temperature by looking at Bett's law, as well as the turbine type efficiency and airflow of the whole farm. Overall, we are very happy with our results as we have zero experience in machine learning, and we believe that we achieved this mainly through very extensive empirical testing. That's all. Thank you to the organizers for this opportunity, and thank you to the rest for listening. We will now open the floor to questions.
Judges?
Thank you, guys. How did you make your model favor under predictions?
Sorry, could you repeat the question?
Yeah, you said that you made the model to favor the under predictions, right?
Yes. So Kwang can go the slides for. So for our normalization, we use bigger values than the denormalization. So in the end, whatever values that we denormalize to will be smaller than the intended values. So if you look at the normalization formula, you can see that for the energy, the mean and the SD are much larger than the values that we use for denormalization.
Okay, okay, so that's all right. And the second question is that how did you, well, first of all, this 5,000 kilowatts, is it the threshold that you set for across the whole time series, or are you introducing it for some particular windows? And how did you set it up at this level?
Go to the. So for the minimum bottom line of 5,000 kilowatt hours, we only set it for the deployment during the live trading, because we noticed after a day or so, we noticed that the values for live trading bottom out at 5,000. So we did not want to waste the 5,000. Yeah.
Thank you.
Any questions from judges?
I have a question. Did you guys use all the data for training or just a portion of it?
We use all the data for training, but we also tried to throw away data for 2017, but it didn't work as well. Yeah. So we use 90% for training for the whole data set.
Hey, just a quick question. So how long did your model take to train?
It took about how long did it take to train?
It took around 2 minutes.
2 minutes, yeah, about 2 minutes.
Okay.
Any other questions from the judges?
Actually, yes. What other architectures did you try before you ended up with 2 layers?
Sorry, what other
configurations of the network did you try?
Of the network, is it?
Yeah.
The slide before this. Yeah, this. So we tried everything on this slide.
No, I understand, but like you tried different network sizes, right? And
yes.
Different layer sizes. So what are these different ones? Like, did you try everything in the world from minus infinity to plus infinity? Or?
So we tried, for network size, we tried from about 16 to 124. And then for the layers, we tried from 2 layers to 4 layers. And for activation functions, we tried these 3 activation functions. And for the leaky value, we tried various values from 0.01 all the way to 0.5. And then for regularization, decay, and dropouts, we also tried a lot of values for all this.
Cool, thank you.
Hello, this is Koi from AI Trader. May you explain a bit like how you find about the correlation between the wind direction and the energy output, please? I think I might miss out a bit.
Are you asking about how wind direction and energy, right?
Yeah. Like, can move on. But I mean, the thing is, can you explain it a bit more, like how you, like any threshold or benchmark that you declare like the strong correlation, or like any method to find this out?
The correlation is just seen from the graph, because you can see that there are peaks at 240, 230, and about 45. And then it starts to go down.
No, I'm talking about the wind direction, like the angle, and versus the energy production.
Yeah. This graph shows the angle and energy production.
Okay, thank you.
Okay, so time is up for Q&A. Thank you, anyhow, Bom.
Thank you very much.
Thank you. Open source, get your slides ready. Anyhow, Bom, can you disable your screen share?
Hi, can you hear me?
Yes, I can hear you.
Okay. Can you see the slides?
Yes, now.
Okay. Good morning, everyone. We are from Team Open Source. My name is Yunjie, and here with me is Farooq, and both of us will be presenting on our group's approach to developing the energy forecasting model. The objective is to play a role of an energy trader and to develop an energy forecasting model for an 18-hour forecast to maximize profits for wind energy producers in the region of Ile-de-France. The trading algorithm is as follows, where our client is paid 10 euro cents per kilowatt hour sold to the grid. If the actual energy production exceeds the forecast, the client is only paid the amount that he forecasted. And if the actual energy production is below the forecast, 20 euro cents per kilowatt hour, which is 2 times the amount, has to be paid to buy the energy to supply for this shortfall. Therefore, it's important to accurately predict the wind energy forecast and to note that the trading algorithm favors under-prediction of forecast as compared to over-prediction of forecast. There are two datasets of wind energy production and wind forecast upon which we will build our forecasting models on, and they mostly represent seasonal data from the beginning of 2017 till now. For wind energy production, it will be in kilowatt hour and standardized to hourly values. For wind forecast, it will contain wind speed and wind direction. There are two different sources for wind speed and wind direction data. However, we have decided to opt out the secondary data for wind speed and direction due to the inconsistencies in updating of the wind forecast. I will now bring you through some exploratory analysis that we have made on the following two datasets. First, the wind energy production. As observed by the graph shown, it's clear that there are two significant shifts in the amount of wind energy output generated over time. After Googling online, we have linked the reasons for the two significant shifts with the construction of two wind farms in two new cities, Bois-de-la-Ville and Angerville. Bois-de-la-Ville wind farm was launched in August of 2017, and before the wind farm was launched, the maximum wind energy generated was around 40,000 kilowatt hour. However, after it was launched in August of 2017, the peaks went up to around 70,000 kilowatt hour. And the same goes to the launch of Angerville wind farm, where the peaks jumped to around 90,000 kilowatt hour. Therefore, from this diagram, we can deduce that the total wind energy output generated varies with the changes in production infrastructure. From this graph, we can also see that the wind energy production is seasonal, where it always peaks at around March and troughs at around June. For wind speed, we can also see that there is a very similar periodic trend, where the wind speed also peaks at around March and troughs at around June. Thus, we can see a close correlation between wind energy production and wind speed. We'll be extracting 4 different types of wind energy indicators from the two datasets, namely wind energy production, average wind speed of the 8 different wind farms, average of cost, and average of sign of wind direction of the 8 wind farms. We decided to use the trigonometry function of the wind direction, as this transformation will make the data for the wind direction more accurately represented and better understood by the model. For example, if there are 2 wind directions that are recorded as 359 degrees and 1 degree respectively, even though it's pointing at the same direction and being only 2 degrees off, it will be taken to be a 358 degree difference by the model simply due to the representation of data in degrees. Therefore, using sine and cosine reduces this discrepancy that is found when using degrees. Before we begin with the construction of the model, we will first need to normalize the 4 indicators as previously mentioned, such that you will have a mean of 0 and a standard deviation of 1. We do this by subtracting the mean and dividing it by the standard deviation. The reason for normalizing our data is because normalizing helps the energy forecasting model learn better, as the raw data set pre-normalization are in very different ranges, and those that are in higher ranges will influence the results more, even though they are not necessarily more important. Now I will hand over my time to Farooq, who will go through our group's step-by-step approach in constructing our energy forecasting model.
Right, so the model that we'll be trying to beat for this competition is the persistence model, which is one of the simplest models there is for predicting the future. With the normalized data that we had, the root mean squared error for the persistent model that we got was 0.445. So this will be the benchmark that we would want to beat for our own models. Moving on to our models, we started off by experimenting with the amount of past data to use as inputs. We tried 5 hours of previous data, increase it to 24 hours, to 50 hours, and even 500 hours of previous data. And what we observe is that generally as the amount of previous data increased, the test loss is seen to decrease. However, with longer sequence lengths such as 500 or 720, we noticed that it took rather long for us to train our models, sometimes an hour or two. Hence, we decided to settle on the sweet spot of 24 hours of previous data, which obtained a decent scores while also trained reasonably fast. Next, we added the wind speed data, which was rather simple. We just simply took the average of the wind speeds from 8 different wind farms in the Ile-de-France region at time t plus 18 hours for us to obtain the forecasted wind speed at the time that we'll be trying to predict. Right, next will be the wind direction. This is very similar to the wind speed in the sense that we take the data from 8 different wind farms, average them out at time t plus 18 hours. But the only difference is that there is a need for us to transform the data using trigonometric functions such as sine and cosine. As previously explained, the data given to us was in degrees. So to achieve continuity and to allow the machine to learn better, we simply just transform the data using the sine and cosine functions. We then played around with train test split. We use a random train test split at 500 sequence length, and the configuration managed to give us a significantly lower test loss for training and validation datasets. However, one issue came up was that when we tried a completely new dataset that was not part of our train and test set, the model was not very able to predict was not able to give a prediction with great accuracy. And this is likely due to overfitting, as we realized that there was an overlap in the train and test dataset. And because of this, we had to go back to a traditional train test split using the previous 70% and the latest 30%. Since there was not much data for us to work with, being only 3 different data sets, which is wind energy, wind speed, and wind direction, we decided to perform some feature engineering to have more focused learning for our model. So we added things like mean, maximum, minimum, skewness, and kurtosis to be inputs for our models. We stuck to using the Adam optimizer as stochastic gradient descent consistently produced a larger test loss. There was a couple of other techniques that we experimented with that did not end up being used, such as dimensional reduction, input scaling, dropout layers, as they did not make our model, they didn't make much improvement to our test loss. And for some cases, it would take a much longer time for our model to learn. So we decided not to use them. So here's the final model that we settled with. These are the inputs for our models and our model architecture. Right, so the model that had the best configuration achieved a test loss of 0.31, which beat the persistence by a decent amount. And we also obtained a lag correlation graph that peaked at 0, which is great. Some of the limitations that we faced was that the data set that was given to us was pre-rounded off to the nearest 500 megawatts, which caused quite a lot of wind energy data that would have been, say, 240 megawatts or 150 megawatts to be rounded off to 0 megawatts. And because of this, we believe that this would have affected the learning and accuracy of our model. Another limitation was the limit of time, where we were given a time limit of 1 minute to run our models and obtain a prediction. So in fear of getting penalized for taking too much time to run our models, if we had 500 input length and all that, we decided against all the longer input lengths and deeper models, and we decided to keep our models relatively simple. Also, with lack of deeper understanding on the more advanced techniques that was being used and taught, such as squared perceptrons, we were not able to very effectively use these techniques, and a better understanding on the math behind such techniques could hopefully allow us to build better models and leave less of the model building to guesswork and trial and error. So some improvements that could have been made was that we could have possibly tried other types of models, such as long short-term memory models, two-dimensional convolutional neural networks, or transformer models, instead of just using our current multi-layered perceptron model. Next, we should have also toyed around with using cube wind vectors instead of the individual wind speeds and wind direction inputs that we currently use, as it will be a more mathematically accurate data to feed our models with because of the physics formulas and stuff, which hence should increase the accuracy of our model in predicting the wind energy.
We also thought of having a penalty feature that penalizes the models for over-predicting the wind energy, which in a sense is similar to what has been spoken a lot of time, creating a custom loss function that would heavily penalize over-predicting rather than under-predicting because of inherently how the nature of how the trading algorithm works. It penalizes more for over-predicting. So with that, I would like to thank AI4IMPACT for organizing this enriching and very much enjoyable Datathon. And with that, I would like to end my presentation. Thank you.
Open source, any question from the judges? Any questions?
I'll ask. What loss function do you use in the end for your modeling?
Right, so we ended up using the basic loss function, which was the mean absolute error. We didn't toy around with using custom loss functions. We didn't really have time to mess around with it. So that was the things that we could have improved on in the future.
Okay. What made you want to try randomized sampling? What's the logic behind it?
The reason behind it is because what we actually started off with is the traditional train test bit, which is taking the oldest 70% of data, and then we are testing it against the latest 30%. But because of the trend that we see is that there's a general upwards trend, the 70% of data tends to cause the model to learn such that it will always under-predict by quite a large amount. So we felt that if we were to use a random train test bit, at least it would have an even representation of the different timelines of data, rather than we are using the oldest 70% of our data to predict the current time and the future time, which will cause some accuracy errors. Yeah.
Okay. Okay, thanks.
Thank you.
Thank you.
Any other questions from the judges? Not yet, guys. Not yet, guys.
Yeah, I'm interested in why did you think about using transformer model architecture to improve it? Were there any papers that you read that inspired you for that?
I think for transformer models, it's generally we heard that it's usually used for NLPs, but because of that, it has like a sort of time series kind of function to it, where it will take into consideration time of the input. So perhaps because of the time series function that transformers allow with the memory that it has from the previous inputs, then it could possibly help produce better performance, but we're not too sure about that. I've only toyed around with LSTMs and CNNs. I haven't touched transformers too much.
Thank you, guys.
Yeah.
You should look into that. It's very interesting how they can be employed for the time series actually.
Yeah, sure. Thank you.
Still have time. Any questions from the audience? Three, two, one. Okay, so thanks so much, open source. So next one is Regen, Team Regen. Can you share your screen now?
Yeah, hi, give me a moment. Okay, are you able to see the slides?
Yes. Before that, let me check with the judges. Judges, so far so good, or you want to have a break, small break, toilet break? Okay, it's good for the judges. So, right, Regen, you can start now.
Okay, great. Good afternoon, everyone. I'm Aiden, and I'm presenting on behalf of Team Regen. So this is a brief overview of our presentation. So after covering the problem statement and objective statement at the start, we will talk about the data analysis and the fine-tuning process leading up to the final model. We will then discuss our implementation approach, some of the model limitations, as well as the suggested improvements. So as we all know, like we have discussed this many times, wind energy is dependent on the environmental factors. So therefore, wind energy is a less reliable energy source in this case. Yeah. So to try to solve this problem, the objective of this challenge is to build a model to accurately predict the wind energy production and to maximize profits for stakeholders such as wind energy producers. So in the context of this challenge, since we are penalized more heavily for shortfalls, our team has noted this assumption and tuned our model to emphasize underprediction of energy. So we first started off with some raw data analysis. For wind direction, we have plotted a wind rose graph and observed that the winds from the southeast tend to produce higher energy output. For wind speed, we noted a much higher correlation with wind energy than wind direction. So the correlation is also the highest when we take an overall average. Yep. Then for the wind energy production, there is a seasonality trend as higher energy production is generally observed between October and March. So after that, we proceeded with the data extraction via AutoCAD. And for the data pre-processing, we first took the average of wind speed and wind direction data from the two forecast models and performed like the spatial averaging on these data. This is followed by the z-score normalization of the energy output and wind speed data. So this is our initial model setup, which only contains the naive window. Like from the losses graph there, you can see that minimal training was done since early stopping terminated most of the repeats. But even so, with the naive setup alone, we have already beaten persistence, as you can see here, using the MAE test loss function. So the predictions were actually quite poor since you can see that the lag correlations peak were at like t plus 18, and the scatter plots also show dispersed data points, which is expected for a naive setup. So we continue to improve our model from here via feature engineering. So one important thing to note for our team is that we decided to adopt a more conservative approach. So even though we did like many rounds of trial and errors for different types of features, we only selected the best features and we did not want to like blindly implement features without proper justifications. So as an example, like for the wind direction data, which are interval in nature, we tried to categorize them into 32 bins. And the bins are then aggregated using average energy output and normalized accordingly using the max output. Then we also tried fitting it with a polynomial regression. And these values were then applied to the wind speed data as a multiplier. However, for our team, we were not able to get any significant improvement in the prediction. So we decided not to use wind direction data as a feature. Yeah. Then for the second feature engineering, we looked into the energy output data, and we made use of a correlation matrix analysis to analyze the first order differential of wind energy data. So we particularly tried out a few different features and looked into diff range specifically, and found that it could help to capture the clustering of the peaks and dips. So we found that diff range with a 12-hour window has the highest correlation with T plus 18 energy. So this helped to increase the accuracy of our prediction and was included as a feature. Yeah, then since wind speed strongly correlates with energy, we derive more features from wind speed itself. So we superimposed the wind speed on wind energy graphs and found that the peaks from both graphs often coincide, even though wind speed tends to vary less than energy. And of course, the first order derivative of wind speed could capture the rate of change, while the second order derivative could capture the curvature. We also modified our models in other ways. Firstly, the red circles that you've seen here shows that there's an increase in energy production capacity, likely due to more wind farms in operation. So for consistency, we chose data from 2019 onwards for our model to learn with data relevant to the current capacity. Secondly, we created an asymmetric loss function, which penalizes overestimation twice as much as underestimation, similar to how potential profit is lost due to excess or shortfall. Lastly, we bound the prediction values with a ceiling based on the past maximum and a floor based on the recent minimum value. So this is this slide actually shows the final configuration and features we have established for the model. So other than the asymmetric function mentioned earlier, dropouts and regularization term were also introduced to prevent overfitting. So here are the outcomes for our final model. Although we cannot directly compare the magnitude of test losses due to the different loss function used, from the losses graph, we can observe that the model has memorized much lesser than the naive model and trains much better. Furthermore, our training and test predictions have a much better data coverage. The data points on the scatter plots are also more compact, while also showing that our asymmetric function, loss function, is working as intended. So most importantly, the lag correlation peak has shifted from t plus 18 to t plus 0, suggesting that the lag has been successfully reduced. Lastly, our estimated profits have also increased significantly compared to our previous models. Yeah, so of course, to fully make use of the model, we have thought of how to actually implement it in real life when we want to, work with it. So we first need to redefine the objective with stakeholders, because we know that in this challenge, all the scenarios are oversimplified in a sense. So there's also a need to understand the complex situations from few experts, and the next step will, of course, to look into data acquisition, where we involve exploring relevant data sources, streamlining the data extraction process, and also analyzing the data to make sure they are up to date. So thirdly, we will look into the model development, and of course, what we have done in this challenge, we will develop and optimize it on AutoCAD, and model fine-tuning and retraining will also be conducted regularly. So after using the models to make the predictions, we will also want to look deep into the interpretation and communicating the results with our clients, so that we can strive to improve based on what our client wants. And the last stage of the development is actually quite crucial also, because we want to make sure that the documentation is done properly to keep track of the model changes and to facilitate the transfer of project ownership. Of course, post-mortem analysis is also necessary for continual improvement. Yeah, so moving on, I'll talk more about the limitations and some of the improvements that can be made for our model. So we found that some active monitoring is required to adapt the pre-assigned floor and ceiling values in real time, because we just set a fixed value. And then these values used in our model were just based on simplistic assumptions of past data. So some of the improvements can be made is firstly, using machine learning to automate readjustment based on seasonal data. Then it is also practical to consult wind farm operators and obtain accurate max output capacity for each wind farms. The next limitation that we observe is that our model is unable to predict sudden energy output spikes that are uncorrelated with wind speed. As highlighted in the red circles here, wind speed may not deviate together with actual energy output due to a multitude of factors. So to reduce this sole reliance on wind speed, what we could do is to diversify the features employed by incorporating data such as air density and deriving more features with wind energy. We could also look into complex effects of wind speed, which I think has been discussed by many other groups as well, in order to assist machine learning. Yeah, so the third limitation will be the opportunity cost incurred from heavy underestimation, which is encouraged by our loss function. So although what our loss function do is provide us with a conservative strategy, the potential revenue forgone during high energy production could actually hinder profit making, as you can see in the gray area, which shows the underestimation during live trading. So to address this limitation, what we could do is to further optimize and analyze the different loss functions that we can use. But in actuality, to actually address this limitation, we will need to, of course, try to improve the prediction accuracy with feature engineering instead. So some of the other possible improvements that our team has thought of is the inclusion of additional weather-related data, which will definitely help in predicting wind energy. We also believe that the hourly wind data could carry more valuable information than interpolated data. And with enough time, I think it will be good also for us to continue optimizing the features, modifying the networks, and also consider a proper weight initialization strategy. Yeah, so that's all for the presentation. Thank you for your attention.
Any questions from the judges? Thank you, Regen.
Can I just check what sort of model architecture did you use?
Okay, give me a moment. Yeah, so for the features, it's actually based on our data analysis. So mainly the four main features are okay, so one of them is the raw data from T+0 to T-6 of the energy feature. Then we also took the raw data for the wind speed features. And as we have mentioned, for energy, we look into the diff range, where we take a 12-hour window for that. And for the wind speed feature, we took the first order and second order derivative. Yeah, so essentially this is our 5 main feature.
Okay. Okay, thank you.
Just a follow-up question. I think what Hanit might have meant is how many layers do you use, how many neurons, etc., right?
Okay, okay, for the layers, I think it was. Oh, okay. I think it was out of the slide. Just let me move back to. Yeah, okay. It wasn't shown here, but so essentially we just followed a very basic feature. Just give me a second. Sure. Yeah. So over here. So we just use so what we tried for the perceptron sizes is actually we did 16, 32, 64, and 128, and then we actually only did like 4 layers for this. Yeah, with a 2/3 reduction. So this is actually similar to what we have learned in the initial stages of our training, and we thought it actually worked quite well. So we also tried varying this layers. We added a bit of layers, and then we tried different reduction, but like they are actually quite similar. So we decided to just stick with this 4-layer neural network. Yeah.
Okay. Okay. Thank you.
Any other questions from the judges?
I have a question about the wind energy and the wind direction. So you, as one of the potential improvements, you mentioned that you probably want to incorporate the air density, which might give you some interesting insights, but probably will not get that much of an impact apart from complicating the situations slightly further. But I'm wondering whether you wanted to revisit your approach on wind direction, really, and whether you have any ideas of what else you could do in order to get more insights from that part of the data set.
Yeah, so I will take that question. For wind direction, we actually attempted to do a trigonometrical transformation using sine and cosine, but then the result wasn't that good. And then for this 32-bit, we actually also tried 108 bits, and yeah, for the above 32 bits and polynomial, we only stopped at the correlation. We thought the correlation wasn't that high, and so we didn't really go further from there. But I think looking back, it could have been a good feature if we further develop on it. And we actually use the normalized weight using from the wind direction, and we multiply it with the normalized wind speed. So kind of to get a vector value. But yeah, we didn't really go far from there. So yeah, this could be a potential improvement.
Thank you. Maybe one more question from the audience. Three, two, one. Okay, so thank you, Regen, for the presentations. You can disable your screen. Last but not least, team JJJY. JJJY, can you get your slides prepared? Okay.
Hi, can you all hear me? Okay,
yes.
Are my slides on the screen? I can't tell. Wait, am I on?
Yeah.
Is it on? No. Okay, it's on already. Yeah. Okay,
yeah.
I'll start now. Okay, good morning. My name is John, and I'll be presenting as part of Team JJJY. To begin, I want to talk about the way our team understood the problem. In this scenario, our team is supposed to play the role of an energy trader that utilizes neural networks to predict the weather and consequently maximize profit for wind energy farm operators. Additionally, we are also provided with 3 data sets comprising of 1 wind energy production data set and 2 wind forecast model data sets. In each of the wind forecast model data sets, we are given data from 8 different locations with 2 variables each, comprising of speed and direction of wind. Immediately, our first thought was to see if there was any correlations between speed or direction of wind against energy generation. What we found was that the speed of wind had a high correlation with energy generation, whereas direction of wind had a low correlation with energy generated. This slide shows you a more visual representation of the results of our analysis. As you can see, the top left and the bottom right, speed of wind has a strong correlation with energy generated, while the direction indicated by the purple boxes have a weak correlation with energy generated. The next thing we did was we wanted to find an appropriate interval for windowing. In other words, we wanted to see if there was any seasonal trend in energy generation, and if so, what was the period of that seasonal trend. The first two graphs are yearly graphs. Straight away, we can tell that the period is less than a month, since we already see more than 12 peaks in both the 2019 and 2020 graphs. Hence, we conclude the period is less than a month. Next, we look at a month. So this graph depicts a month. The red boxes on the graphs are used to indicate a week. And from what we can see, there was no seasonal trend, there was weekly. What we could conclude was that the period was probably less than a week. Next, we do a week. So the next graph has red boxes that indicate periods of more than 24 hours, while the blue boxes indicate periods of exactly 24 hours. At this point, we concluded that the period was probably more than 24 hours, but not much more. What we hoped for was for a period of the seasonal trend to be as low as possible in order to obtain more sets of values after feature selection, which would result in more data, which would be beneficial for neural networks. We also came to the conclusion that for feature selection, we should consider the following values: minimum, maximum, mean, standard deviation, range difference, and skewness. After a rough sensing of our data, we did a benchmark test with the provided configuration, changing the neural network very slightly. From the benchmark, we got a test loss of 0.48, a useful value to gauge our progress as we move forward. The next slide shows a scatter plot of the actual versus training and actual versus test predictions for our benchmark. The important thing to note is that the data points appear to be scattered around and are non-linear. In this slide, the important thing to note is that the lag correlation peaks at 17, which is bad, since that would mean our forecast will be lagging behind by 17 hours, which is not optimal. Before we start building our model, I want to stress certain points. First, not all of the data given are as useful as we thought. Wind direction in particular should not be a focus in our model due to the low correlation with energy generation. Second, the range is more than 24 hours, but not much more. More importantly, we should seek to minimize the feature range. Third, features transformation should consider mean, max, mean, standard deviation, range difference, and skewness. Lastly, this is something we always try to keep in mind. We should try to keep the model as simple as possible. To begin our model building, we did data extraction. Here, keeping all other configurations constant, we slowly attempted to reduce test loss. In the process, narrowing our data sets to the most optimal data set that achieved minimum test loss. In this case, we narrowed our data down to using all 8 wind speed and 2 wind direction data sets from model A. Before we did testing for our features, we normalized our data and calculate the root mean square error persistence value that we had to beat. We found the value to be 0.44, lower than our benchmark test loss of 0.48. Unfortunately, our benchmark did not beat persistence. On to feature engineering. Here, we found that the optimal lead time was t plus 18, which was the predefined lead time. We tried t plus 24 and many others and found that those lead times had a higher test loss than t plus 18. Through incremental testing, we also found that the optimal feature range was 40 hours, not far off from our prediction that it would be close to 24 hours. We also realized that the mean, max, range, and skewness actually contributed to an increase in test loss, hence we chose to exclude them and make our model even simpler. At the end of our testing, these are the settings which produce the lowest test loss we could achieve of 0.21. Using mean and standard deviation of range 0 to negative 40 for all columns, since the optimal feature range was 40 days, we also used the lead time of t plus 18 and the difference based on range 0 to negative 40. Now that we are done with processing our data, we'll move on to the way we define our network. First, we found that the optimal solver was the Adam solver. Next, we tried experimenting with a dropout layer and found that the dropout probability of 0.05 was better than 0.1 and 0.3. Curious about whether our test loss will decrease if we decrease the dropout probabilities even more, we tried to manually insert dropout layers that have probabilities far lower than 0.05. Surprisingly, we also found that it actually did reduce training and test loss. As such, we concluded that we probably should make our dropout probability as low as possible. Moving on to neural network size, we tried 16, 32, 64, and 128. We found that 32 and 64 were the optimal sizes and minimized test loss. Next, the activation function that worked best was ReLU. Optimal weight decay was found to be 5 times 10 to the power of negative 6, and optimal regularization was L2. We also set repeats to 25 to keep the results consistent and reliable. To prevent early stopping, we set iterations to 10,000. This slide shows a more visual representation of our network. As you can see, it's a 5-layer network, which has a 2/3 reduction in size over layers. The there are two dropout layers between the first and second network layers that have a dropout probability of 0.0001 and 0.0005 respectively. Once again, we use ReLU for the fastest and most optimal results, as well as set the weight decay to 5 × 10 to the power -6 and regularization to L2. Here you can see we achieve a test loss of 0.21. Here you can see our actual versus training and our actual versus test scatter plots have points that appear to be linear, which is a positive result. As for our lag correlation, it peaks at t = 0, which is a positive result as well. Finally, you see our net profit, which we believe is quite good. So we will talk about the limitation of our model. First, we could have achieved a lower test loss if we explored more data transformation techniques like interpolation, spatial averages, and many more. Second, our model also kept overestimating energy generated when the actual energy generated was lower than average. The second point I made is especially important because during the contest, we tried to figure out why our model was doing badly, especially during periods where energy generated was low. What we found could be useful information for improving our model. Trying to learn from our model forecast, we plotted the following graph. The graph shows our forecast in orange and the actual energy generation in blue. Below, we put a graph of humidity to find if there were any correlations between energy forecast and humidity. Humidity is also usually tied with weather, so out of curiosity, we decided to analyze weather as well. As such, we did our analysis with humidity as well as weather data, and here's what we found. On the left, you see a pie chart that shows the distribution of the weather when our model was making losses. We can conclude that the majority of the time when our model is making losses, there will be passing clouds. As such, it is irrefutable that weather has an impact on energy generated. On the right, when the graph is below the orange line, there are losses. The red rectangle highlights the fact that when there's a dip in humidity, there were losses made by our model. Hence, upon knowing that humidity as well as weather plays a crucial role in undermining our model, we could learn from our mistakes by including weather data as well as humidity data in the future to make our model more robust. Question and answers. Nice. Oh, sorry.
Okay. Any questions from the judges?
Can I ask a question? The humidity data, where did you get that from?
We got it from an online website.
Okay. Yeah, thank you. That's pretty good that you guys sourced that and could make a correlation. That's okay. I don't need to see the actual data source. I was just wondering where you got it from. Okay, so it's.
Any other questions? Maybe I'll throw it to the audience. Or other teams. Any questions? Maybe a burning question before, we end our team's presentation. So. Okay. Going 1. Going 2. 2.5. 3. Okay. Thanks so much, JJJY. Maybe you can disable your screen share. All right. So 10 groups, 10 presentations, and we are finally 8. So maybe before, let us give some time for the judges to make some decisions. So what we'll do next is that judges, we will send you to breakout rooms where Arnold, Hanif, and Dr. Misha will actually have internal discussions. For you guys, we'll have a 1-minute toilet break. So yeah. So let's have a break for now. Let me just send. Okay. Let me just get. Okay, so all judges are in breakout rooms. So they will be actually like, they will be summing up their marks right now. So while we are waiting for the judges, maybe I can just have some comments I think from fellow students who just graduate as well. So they do have their technical comments. But I think for me, what I can say that all of you are actually are doing very well, including the top. Okay. I think we have some, okay. Some disco there. Okay, so I think overall all of you are doing very well. But having said that, I think from you, Koi. Yeah, having said that, this journey doesn't end, and I think for you guys, to just like get your results done in a competition setting, I think it's not enough. One advice that I share with for you guys is that you guys are already like showcasing good results, and I think but there's no use having good results without like having a lot of people know about it and your achievement as well. So one thing that I strongly advise you to do right after this, right, is actually to because you guys actually are writing Medium articles, it's not just for us to check whether like your results are valid, but also for you guys to actually like have some tangible result that you can showcase in your personal portfolio page, because some of you are now still students. A lot of you are students, and some of you are also like someone who are exploring career in data science, right? So we do actually like based on our past students, we do get a lot of them saying that they get some engagement from both government and private sectors because they happen to read their Medium articles, and their Medium articles are also shared on their LinkedIn page as well. So everybody somewhat knows that you are already achieving. You are not just achieving something. You are learning something from scratch. You are building the models within one month. You are also like deploying that models, and you are making some profits based on some kind of like real life simulated real life situation. So one thing that I encourage you to do is to actually directly share your articles on your LinkedIn page as well, because that you should be proud of it. And I think for all of you, especially those who are not in computer science, right, that gives lots of windows and credibility for you to pitch yourself to in front of the employers. Because just have a sharing from our side, because we also work with a lot of employers, SG Innovate included. I think for SG Innovate, if you look at the comments from Mr. Hanif and Dr. Misha, they are someone who are very clued up. So they know actually like they can separate good students and good talents, and also like not so good talents, regardless of their resume. But that kind of talents, that kind of employers are quite rare. And what you want to do is that you want to use this, right, as an indication of your capabilities. Something, because from our experience, right, a lot of students actually learn a lot of stuff from online learning. A lot of them actually take some courses and all that, right, and they showcase their certificates. But to be honest, like from the employer perspective, many actually like because certificates are quite common these days, but students who are able to showcase some results and especially like have some kind of deployed some models, right, are pretty rare. So that gives you competitive edge over others who are just learning. So I think what we truly strongly encourage you to do is to actually publish your Medium articles on your personal page, and then also maybe like have some kind of like connection with the with industry experts. I think some of you actually like indicate interest to talk to the judges, right? I think that's good initiatives, because from there they might actually possibly mentor you lah. But in exchange, maybe they will ask you to do some free work as well, some exploratory data work. But I think it's worth it because they are actually the right industry mentors. And before you graduate, you have some good industry mentors, right? I think it gives you strong competitive edge in terms of knowing what to do next, or which modules is important, right? Or what subjects are important to learn, which online courses should I take, and then which projects should I do as well. What is important for in real work? Is it really the accuracy, or is it really like the speed of your deployment as well? because I think I know that from Hanif that high frequency traders actually care a lot about latency. They are playing around in a nanoseconds or milliseconds game, so that is actually takes precedence over sometimes the accuracy of your model. So I really want you guys to actually build your own path of success, showcase what you do, because what you are doing right now is non-trivial. And I know you guys actually have worked really hard. We actually grilled you hard as well for these competitions. Be proud of it and showcase your results. So I think that's my perspective as well, because we heard from our students that some of them actually get employed by a defense R&D organization in Singapore because they publish their dengue results, which is where Caitlin spoke about on the Medium articles, and someone happened to read it. And I think also some of the team that is here, right? Some of them actually get their articles actually nudged. I mean, they were nudged by towards data science, which is quite one of the most famous Medium publication, to share their articles to their bulletin. And I think that's a big deal because you get a lot of traffic for your own personal portfolio, right? So I really encourage you, Medium is a start. Doing more projects is another thing, but make sure that what you have worked hard for the past month is documented and also published on a public space. So yeah, that's why I think on our end as well, we also try to create a profile page. It's still our MVP, but what we hope is that from that profile page, right, we are actually going to share it to our own circle of employers as well. So on our newsletter, I think some of you received our first 2 newsletter. That one actually there are some employers actually following up that, and we want to feature also your results. So not just for employers, but also for others to learn from you guys. So what I strongly advise you is that try to maybe create your profiles, if not on our platform, at least on LinkedIn, because a lot of HR people are from LinkedIn. We also get, I think, we also connected with renewable energy employers, very specific on renewable energy trade. So she's actually keen to see the results of the Datathon. She's watching it, on YouTube Live. But what she wants to do is that if she also is looking for good talent lah. So if you guys actually showcase your portfolios continuously, right, then you are somewhat, naturally separating yourself from other students who are just stop at learning, because at the end the companies are looking for problem solver instead of learners, right? I think something that you have to point out. And I think at this stage, based on your presentation, I'm quite confident that you guys are able to responsibly share our result lah. So you guys know what you are doing, and you guys know what to say as well. So that is a big plus for employers. So I think that's a sharing from our side, because we have some. I think Caitlin also was our winner as well. She was a year one student from mathematics, and she just started actually learning data science from there. But she somewhat get hired by SG Innovate data deep tech program, because she showcased her results, not just results, but her own app as well. So the employers can actually see can play around with the dengue models. So I think that's our vision based on our experience as well. And I think it's good to relay this to you guys to see to understand how important it is to have your own project portfolio. But I think you guys are doing very well. It's a live forecast models. It's not it's not a small thing lah. Even I'm also trying to reach that level yet. I'm still learning because Arnold give me a lot of work, so I don't have time learning this. But I hope to actually emulate your result as well. So I'll personally learn from you guys. Looking forward. It's a tough competitions. I think I happen to look at the results a bit. It's a very tough, it's very close call. So let's see what they will say lah. It's a very close, very close call. So let's see. To be honest, let's see. Maybe some of you want to say something while we are waiting for the judge.
I'd just like to say that overall, we've been working on this project for a month, and it has been a really great learning experience. So for our teams, AI traders, half of us came from a tech background, and half of us did not know anything. And it was a good experience to start something from the start something from the downright basics, and build it up. So from our team, I'd just like to thank you and the other organizers to actually teach us and like help us build this entire model.
Right. Thanks so much, yes. Actually, the problem set actually is based on our conversation with energy company, like energy producer company in China, actually. So we actually, for them, right, if I think a lot of people have misconception on what financial prediction is like. Sometimes financial prediction is not just about predicting the stocks or commodities as is actual, like value, right, price value. So what they are doing, actually they are looking for some signals, right, that gives them much more reliable buying decision. And sometimes, like if you know the trading, if you know the environment, right, the ecosystem, right, sometimes like the best way actually is for them to find out some derivative information that will lead to reliable decision making, whether they want to should buy or sell. And this is like their strategy actually on actually how they buy or sell energy, because they are playing on that instead of relying on fluctuation on the price, right? They're relying on that to get much more reliable trade lah. I think that's one of it. We also try to work on commodity forecasting, but again, I mean, for you guys, like what's next, right? For you guys, right? We do have some ideas, but it's now, I think, be patient, because we have some we are looking for data sets that has no copyright issues as well. Because if needed, and if you guys are really interested, right, if we get some audience for the next Datathon, we are even thinking on purchasing a commodity data for you guys to play around. We will try to get as much as possible as live as possible. So that means that we subscribe data, and the data keeps on pumping in and out. And let's say if you guys make profitable trade, and we can profit share lah. From my point of view, like keep me in touch, then we can profit share based on your commodity forecasting algorithm. But I think I'll keep in touch with you on the next idea. We are still scouting for the best data sets to play around, and the best problem set as well. Okay, so so they are done. They mentioned that they have a special mention, so it might not just be a top 3. Let me just get them on board. Let me just how to get it. Close all. Okay, so they are done. Okay. Okay, all the judges are here. Arnold, maybe you want to start?
Okay. Well, guys, it was actually a hard decision. And I think all of you, can you guys hear me? Am I mute again?
Yes, clearly.
Okay, so it was really good. We were all happy with the results. And I think the judges came to a consensus in the end. Okay, so we have an extra team which we would like to put for special mention. Okay, so I'll go from team number 4 with the special mention all the way up to the champions, right?
Wait. Maybe can you give overall evaluation first, just to get the suspense going?
Okay, why don't we ask one of the other, because I've been talking to you guys nonstop for the last few weeks. So maybe we're going to give maybe Hanid or Misha the opportunity to say something first.
Yeah, sure. Yeah, first of all, I'd like to thanks AI4IMPACT and obviously SG Innovate for inviting me. I don't consider myself as a machine learning expert, although I'm actually picking this up, taking a few courses, and obviously our startup involves a lot of natural language processing. So I know this domain's not really easy. There's a lot of solutions out there, a lot of papers. So I saw 10 teams today, and I think a few teams mentioned that they just picked it up and entered the competition and still ended in the top 10, which is, I mean, that's a really good achievement. And all of you presented very well, I thought. And everyone had like very good data visualization. It was easy to follow. So yeah, I was quite impressed, very impressed. So yeah, that's it from my side.
Dr. Misha, maybe you have something
Yeah,
to say?
maybe I can say a couple of words too. So first of all, thank you all the teams for putting so much effort into that. It's not a trivial problem because, well, although you can, this business is quite profitable, as probably you have learned by now already. There is not a single solution, that no silver bullet actually in that. And if you dig deeper into papers, then there is almost an infinite amount of other data sets that you can add on and other parameters that you can add on in order to improve your model and go deeper and deeper. It also, they will be very different in different regions, etc., etc. So if you are interested in this problem, actually, you can go very deep. You can do a PhD, and after that, like it could be your career in total. At the same time, without knowing much about the physics in this direction, you did show some very interesting results, very impressive actually ones. So it was really difficult to judge, which is always a very good sign. So it was, thank you for that. Thank you for making it interesting, and very good job. So at the same time, remember that you can go far just on your skills, machine learning skills, with an analysis, just analyzing the data and really keep showing the best patterns and a lot of insights from the data. But without deep understanding of the domain, it's very often difficult to make a leap. So when you really want to make this an extra advantage from your competitors, it's usually when you have to look into really why certain things are happening. And I encourage you to do that in future on whatever future projects you're working on. So not just look at the data, but really try to understand what's really going on, what are the underlying processes, and why certain things are even happening in the first place. But thank you very much. It was very interesting.
Thanks, guys. And now we come to the results, okay? So we have a team for number 4, or special mention, and that would be AI traders. You guys did a good job, and we thought that we need to recognize that work as well. All right, so AI traders, number 4. Number 3, Stonks. Number 2, Anyhow Bomb. And number 1, Triple JYE, right? All right, so congratulations, guys. Chris, I'll pass it on to you now.
Okay, maybe before that, you want to have some kind of explanations. What do you like about the top 4, and what you see, like what's the X factor from the top 3, 4, 3, 2, 1, or especially the best one?
Okay, so it was very clear. I think for AI, let's go from the bottom up, right? So I think AI traders, I think you guys did. I think the goals were very clearly defined. You wanted to look at reliability and stability of the model. And generally speaking, I think you would definitely achieve that, right? I think at the risk perhaps of being slightly cautious, I think the goals were clearly defined. We liked the analysis, and you guys did a good job. The presentation was very good as well. Stonks, you guys did very well. you tried a lot of models, right? But the models are also pretty complicated. And I think for us, maybe where you guys didn't do as well was really maybe, did you understand really the reasons behind those things, the reasons behind why things worked and why it didn't work? That didn't come out so clearly in your presentation. Okay. Anyhow, Bomb, what we liked was, I think Misha and I liked the fact that you guys incorporated a physical model and then tried to look for justification for that model using the data science. I like the fact that you've got a simple model, which really does very well, right? And I would say that performance-wise, I would say Anyhow, Bomb and Stonks were about the same because you guys were flipping up and down, right? The winner, Triple J, I'm sorry, is it Triple JYE or is it Triple JY? Triple JY, that's right. Triple JY, you guys, what we really like, all three of us, was the fact that you introduced other factors outside of the competition, things like, the weather factors, etc., and so on. The model was fairly straightforward as well. And I think the amount of data you use was also, not really very complicated. And you seem to demonstrate a better understanding. And your data analysis was also pretty good too. So I think it's overall, I think there was a broad-based positives that you had in many different things, which is why we decided that you guys were definitely, the #1 team.
Okay, so first of all, I think we want to say congratulate the 4 teams for winning the competitions. It's been hard 1 month, and I think you guys, I would say all of you are doing very well. But I think let me on behalf of AI4IMPACT and also the students, let us also appreciate the time taken by the judges, Dr. Misha, Hanif, and Arnold as well, for judging the competition as well. Yeah. So these are they're all very busy. Dr. Misha is running a company. Hanif is actually doing a lot of technical works. And Arnold, he's my boss, so I'm obligated to. Okay, kidding. So maybe let's give a round of applause for virtual applause to the judges as well. Yeah. Okay. So before we end, I'd like to, since all of us are here, maybe all of you can enable your screen, your video. We can have a nice photo shoot together. Can all of you enable the video? No video, no certificate, guys. No, kidding. I think you guys have your own, your certificate is your Medium article as well. Don't underestimate the power of your public article, publicly available article. Okay. So yeah, I can see you, Limang, Solo Leveling, Team Maverick, Anyhow Bomb. Solo Leveling, can you switch on your camera? Anyhow Bomb as well, and John VJ, winner.
See, no camera, no camera.
Oh, no camera. Oh, okay. That's unfortunate. Okay. Just thumbs up. 1, 2, 3, thumbs up. All right. Okay, one more. 1, 2, 3, thumbs up. Okay. Okay, thank you guys. I think maybe a close-up announcement. The certificate, we'll print you the certificate shortly, so you will receive the e-certificate by we are actually getting Innovate to sign the certificate as well, so give us some time to do that. The second thing is that this is not this is just the beginning for you to explore more AI projects, and also I think some of you have expressed your interest to connect directly to the expert as well, including the judges. Maybe we'll try our best. So Hanif, Dr. Misha, if they say they are keen to ask questions or connect, I'll maybe just connect with you separately, just on an email. Yeah. And last but not least, we do have the leaderboard now active, and we are going to reset the leaderboard soon. Your model is still plugged there, fortunately and unfortunately. So you can see your results actually on your live leaderboard. So the leaderboard will be officially resetted today, and tomorrow you'll have a fresh, fresh results from your own deployed. So if you want to see that how your model is performing over time, please look at the leaderboard page. And I think also we have a August edition of these competitions where you can actually maintain your stronghold in this in this live tournament, because we have new fresh talents as well coming in to challenge your standings right now, your ranking. So I'll give you more announcement on that. But all in all, I think all job well done. So officially now we want to close. Okay, Arnold, you have something to say?
Yes, you want to mention, Chris, about the next week thing where we have a wrap-up event. Just if you have any questions or any things, right? I feel that many of the teams here, although you're in the top 10, there are some missing aspects in what you're doing. And I think that needs to be discussed and clarified if you're serious about learning from this, right? For example, I think it was either Misha or Hanit asked you guys, why is your model under forecasting? Actually, a lot of your models are under forecasting as well. And I don't think anyone gave us a clear answer, okay? And it's actually very obvious to me why your models are under forecasting, all right? So if you want an answer to this or anything else, and I think there are quite a few other things that you can ask, right? I think take the advantage or take the opportunity to just join us for a very cozy Zoom meeting where you can ask questions in live. And I'll also try and I think Chris will organize a Q&A as well that you can actually post, and we'll probably answer the questions then. Okay?
Yeah.
So this is the start of your journey, guys. AI, I think a lot of you have just begun, right? Right? I'm actually pretty amazed at how many zeros to heroes we got out here, man. All right? So congratulations.
The gap between the benchmark and your results actually are pretty high, which is surprising for newbies in a way. So it's just a start. It's just a little bit more to making more money on your real life using your own forecasting model. So it's just hopefully it's a little bit more to making money from your forecast models. But all in all, Datathon now is officially ended. We want to thank all parties who are involved, as Innovate as our deep tech partner, fellow judges, Dr. Misha, Hanit, and Arnold as well, for your time, your very precious time guiding the students. And all of you guys, most importantly, all the students who are doing very, very, very well, extremely well. It's a deployment model, and you guys actually managed to make profit out of the simulated real life model. So a huge congratulations for all of you. Have a good rest for today. We have some more things planned up, so we will keep the Telegram group going to announce new events, to keep the community going as well. So have a good day and see you next time.